Ferrero Rocher, Cadbury Dairy Milk, and Maltesers are legendary chocolates known for their rich flavors and unique textures. From delicate hazelnut layering to creamy milk chocolate molding and aerated malt centers, each treat is crafted with specialized machines and precise techniques. In this video, we uncover the fascinating process behind these world-famous chocolates and reveal how they're produced on a massive scale with flawless consistency. Ferrero Rocher begins with hazelnuts, each one carefully selected for size and quality. Inside the factory, the air smells faintly nutty even before anything is roasted. Conveyor belts carry mountains of hazelnuts forward, tumbling them through giant roasters. The heat turns their pale skins a golden brown, filling the room with the rich aroma of toasted nuts. Workers say it's one of the best smells in the candy industry. Warm, earthy, slightly sweet, a fragrance that clings to your clothes for hours. The roasted nuts rattle down metal chutes and through high-speed sifters that shake off any loose skins. Jets of air blow away the papery husks, leaving behind glossy, golden kernels. From here, the hazelnuts split into two paths. The most perfect specimens will become the whole hazelnut cores at the center of each Ferrero Rocher. The rest will be ground into paste, forming the silky filling that surrounds those cores. Nothing goes to waste. Every hazelnut finds its place in the system. On one side of the factory, the chosen whole hazelnuts pass through sorting machines that measure them with laser precision. Too small, too large, or slightly chipped, and they're set aside. Only the most flawless nuts earn the right to sit at the center of a Rocher. On the other side, roasted nuts are crushed between steel rollers, then refined into a smooth hazelnut paste. This paste is blended with cocoa and milk powders, forming a creamy chocolate hazelnut filling not unlike Nutella, but richer, thicker, and made specifically to cling to the core. The assembly begins when trays of delicate wafers enter the line. These aren't flat wafers like you'd find in an ice cream cone. They're hollow hemispheres, paper thin, crisp, and perfectly round. They move forward in pairs, ready to enclose the filling like two halves of a shell. In the first stage, a nozzle deposits a swirl of chocolate hazelnut cream into the base hemisphere. A roasted hazelnut drops into the center, sinking slightly into the filling. Another swirl of creme covers it, ensuring the nut is fully cocooned. Then the second wafer hemisphere drops on top, sealing the core into a fragile ball. At this point, each piece looks like a pale, round wafer, fragile and unassuming, but the transformation is only beginning. The wafer balls travel down the line to chocolate coating stations. Curtains of molten milk chocolate cascade downward, drenching the wafers as they roll through. The chocolate clings to every ridge, filling in gaps, hardening into a glossy shell. Before the coating sets, another layer of hazelnut magic is added. Chopped hazelnut pieces rain down from hoppers above, sticking to the still wet chocolate. They tumble and cling to the surface, giving the candies their signature bumpy texture. From above, it looks like a golden brown storm, bits of roasted nuts falling onto spinning orbs of chocolate. As they roll forward, the coating thickens, turning fragile wafer spheres into sturdy chocolate hazelnut truffles. Cooling tunnels blast the chocolates with chilled air, locking the coatings in place. Conveyor belts stretch like highways, carrying thousands of finished orbs through refrigerated chambers. By the time they emerge, the chocolate has hardened to a crisp snap, the chopped hazelnuts embedded like jewels on the surface. Workers inspect them for uniformity, pulling out any that don't meet the perfect round standard. But Ferrero Rocher is not complete without its most iconic feature, the golden wrapper. Packaging machines pick up the cooled chocolates one by one, dropping each onto a square of gold foil. Robotic arms fold the foil tightly, twisting it into place with mechanical precision. The sight is dazzling, rows of brown and gold forming in unison, plain chocolates transforming instantly into sparkling treasures. The wrapped pieces tumble into paper cups, their ridged bases cradling each one like a tiny pedestal. From here, The cookies and chocolates are arranged into familiar formations, neat rows in transparent boxes, stacked pyramids for gift displays, or smaller packs for everyday indulgence. Every arrangement highlights the golden shine, reinforcing the image of Ferrero Rocher as more than a candy, almost like jewelry you can eat. The packaging process is fast but elegant, designed to protect the delicate chocolates while enhancing their luxury aura. The genius of Ferrero Rocher lies not only in its flavor, but in its engineering. The wafer layer adds crunch without bulk, light enough to shatter instantly under your bite, but strong enough to protect the creamy center. The hazelnut filling is smooth but firm, holding shape until it blends with the chocolate shell in your mouth. The whole hazelnut core provides a surprise crunch at the center, anchoring the experience with contrast. Every layer, wafer, filling, nut, chocolate, chopped hazelnuts, was designed to arrive on your tongue in perfect sequence. From the catwalks above the production floor, the scene looks like a golden factory symphony. Conveyor belts shimmer with glossy chocolate orbs. Curtains of molten chocolate pour endlessly, coating the wafers below. Streams of chopped hazelnuts rain down like edible confetti. Cooling tunnels hum with cold air. And in the distance, packaging machines crinkle with the sound of foil wrapping snapping into place. The smell is intoxicating, a blend of roasted hazelnuts, melted chocolate, and freshly baked wafers that seems to follow you even after you leave. Durability is part of the design too. Despite their delicate look, Ferrero Rocher are engineered to travel. The wafer protects the filling, the chocolate coating seals in freshness, and the foil prevents exposure to air and light. That's why they can cross continents, survive shipping containers, and still taste as crisp and luxurious as the moment they left the line. Even the paper cup beneath each one serves a function, preventing the spheres from rolling in transit while adding an extra layer of elegance. Seasonal variations and spin-offs run down similar lines. Some factories produce Ferrero Rocher with dark chocolate and a crisp pearl inside. Others make Ferrero Raffaello, swapping hazelnuts for almonds, coating them in coconut flakes. Each follows the same principles: wafer shells, creamy fillings, nutty cores, chocolate coatings, adapted to different flavors. Watching multiple lines in action feels like watching cousins being born side by side, each distinct but clearly part of the same family. If you slow the process down to a single piece, the craftsmanship becomes clear. A roasted hazelnut is placed in a wafer half. A swirl of hazelnut filling surrounds it. Another wafer half seals it closed. Molten chocolate drenches the sphere. Chopped hazelnuts cling to its surface. Cooling air hardens the shell. Foil wraps it in gold. A paper cup cradles it. And just like that, in under a minute, a Ferrero Rocher is complete. Multiply that by millions, and you have a factory ballet that never stops. When you open a box, that journey hides beneath the shine. The crinkle of foil as you unwrap. The snap of chocolate giving way to wafer. The flood of hazelnut cream blending with the crunch of nuts. The roasted core at the center, a final burst of flavor before it all melts away. That sensory sequence, the crisp, the cream, the crunch, the melt, is the moment the factory is designed to deliver, repeated flawlessly around the globe. The next time you bite into one, picture its path. Hazelnuts roasted golden brown, sorted with laser precision. Wafer hemispheres pressed into perfect shells. Swirls of filling, cocooning whole nuts. Molten chocolate pouring over fragile orbs. Hazelnut fragments cascading like rain. Cooling tunnels humming with cold air. Golden foil snapping into place. Rows of chocolates arranged like treasure in transparent boxes. All of it engineered to deliver one bite of luxury. Cadbury Dairy Milk begins with milk. Not a splash or a carton, but tankers full of it. Rolling through the English countryside and arriving at the factory gates every morning. The trucks back up to stainless steel silos taller than houses. pumping thousands of gallons into storage tanks. Inside, the air smells faintly of cream, sweet and slightly grassy. The aroma of fresh dairy before anything has been added. This is the first ingredient, and the one that gives Cadbury dairy milk its name, its flavour, and its famously smooth texture. The milk is pasteurized and evaporated, turned into a rich condensed form. Steam rises from enormous vats as water is driven off, leaving behind a thick, creamy concentrate. From above, it looks like rivers of custard, glossy and pale. This milk concentrate is then blended with sugar, forming a sweet, golden mixture that will later crystallize into the backbone of the chocolate. Workers describe the smell here as a mix of warm caramel and fudge, a fragrance that drifts through the entire facility. Meanwhile, cocoa beans make their own journey. Shipments from Ghana, where Cadbury sources much of its cocoa, arrive in massive burlap sacks. The beans are poured out in avalanches, rattling across vibrating sorters that sift out stones, sticks, and anything that doesn't belong. Fans blow away dust, leaving clean, glossy beans that smell faintly of fruit and earth. They roll forward into colossal roasters, steel chambers glowing with heat. The beans tumble inside, their skins cracking, their flavors deepening, the air filling with the unmistakable smell of cocoa. Once roasted, the beans are winnowed, cracked open, their papery shells blown away by air, leaving only the nibs. These nibs are crushed into cocoa liquor, a thick, dark paste that shines like molten tar. At this stage, it's bitter and strong, but it carries the essence of chocolate. Tanks hold this liquor warm, waiting for the moment it meets the sweetened milk concentrate. In the mixing halls, the two streams finally come together. Pumps force the cocoa liquor into giant steel vats, where it blends with the sugary condensed milk. The mixture is heavy, sticky, almost dough-like. It clings to the sides of the mixers in dark, sweet clumps. Workers sometimes call this stage chocolate crumb, a coarse, sandy mixture that doesn't yet melt like chocolate, but carries the foundation of its flavor. The crumb is dried, cooled, and stored in vast silos. When needed, it's reintroduced into the refining line, where rollers crush it again and again. The rollers stretch longer than cars, massive steel cylinders spinning in opposite directions. As the crumb passes through, it flattens thinner and thinner, transforming into a fine, soft powder. You could scoop it up like flour, and it would taste sweet and cocoa-rich, but still lack the smoothness of chocolate. Smoothness comes from conching. In long, shallow troughs, giant paddles stir the chocolate powder with cocoa butter, milk fats, and emulsifiers. Heat and motion break down particles, release trapped acids, and polish every grain until the mixture transforms from gritty powder into flowing silk. The machines churn for hours, sometimes days, the sound a steady rumble like waves on a shore. Standing nearby, you'd smell roasted cocoa mellowing into creamy chocolate, the harshness fading into something soft, rich, and comforting. From the conchas, the chocolate flows into tempering machines. Here, the temperature is raised, lowered, and raised again in carefully controlled cycles. The purpose is crystalline perfection, ensuring the cocoa butter molecules lock together in the right form. Without tempering, the chocolate would look dull, streaky, or crumbly. With it, the chocolate emerges glossy, snappy, and stable, the kind that breaks cleanly and melts luxuriously on the tongue. Now comes shaping. Stainless steel depositors hover over endless molds, rows of rectangles, each engraved with the Cadbury logo. With a hiss of air pressure, streams of liquid chocolate squirt into the molds, filling them in perfect measure. The molds vibrate to shake out air bubbles, the surface rippling until it levels smooth. From above, it looks like rows of glossy mirrors, dark brown and gleaming. The filled molds ride conveyor belts into cooling tunnels, long refrigerated chambers where chilled air circulates constantly. Slowly, the chocolate sets, shrinking slightly away from the edges of the mold. By the time the bars emerge, They're solid, glossy, and stamped with the Cadbury mark. Machines flip the molds, releasing the bars with a satisfying clatter onto padded belts. A quick inspection removes any imperfect pieces. Bars with bubbles, cracks, or smudges never make it to the wrapper. The perfect bars continue forward into wrapping stations. Purple foil crinkles and snaps as high-speed machines fold it around each bar, followed by a paper sleeve that slides neatly into place. The sight is iconic. Rows of rich brown chocolate disappearing under flashes of Cadbury purple, transforming into the bars you'd find on a shelf. Packages are stacked, sealed, boxed, and loaded onto pallets. Forklifts whisk them away, ready for trucks that will carry them to stores around the world. What makes Cadbury Dairy Milk unique isn't just the process, but the ratios. The milk to cocoa balance is tuned differently than most chocolates, leaning heavily on dairy richness. That's why the bar feels creamier, melts faster, and carries a sweeter flavor profile. It's designed to be approachable, comforting, indulgent without being overwhelming. The smoothness comes from milk fats, the sweetness from the crumb, the balance from generations of careful tweaking. From the catwalks above the production floor, the scale is breathtaking. Silos taller than houses hold milk crumb. Roasters glow as beans tumble inside. Roller refiners hum with constant motion. Conches stretch like swimming pools, filled not with water, but molten chocolate. Cooling tunnels hum like wind tunnels, exhaling chilled air, and everywhere, the smell. Sweet, milky, chocolatey, clinging to the walls, the air, and even the workers' uniforms. Variations of dairy milk roll off parallel lines. Fruit and nut bars, where conveyor belts shower raisins and almonds into molds before the chocolate sets. Caramel bars, where golden streams of liquid filling are piped into half-filled molds before a chocolate lid seals them shut. Buttons, mini bars, giant slabs, all use the same tempered chocolate, adjusted only for shape and filling. Watching these side by side is like watching different instruments playing the same song. The melody of chocolate adapted for every audience. Durability plays a role too. The tempering ensures that dairy milk bars resist melting too quickly in stores, while the foil and paper protect them from light and air. That's why a bar bought in London, Mumbai, or Sydney tastes the same, even after weeks of travel. Consistency is a promise, and the factory delivers it through precision at every stage. If you slow the process to a single bar, the craftsmanship becomes visible. Milk condensed into sweet golden concentrate. Cocoa beans roasted, cracked, ground. Cocoa liquor blended with crumb. Powder refined through rollers. Molten chocolate stirred in conches until smooth. Tempered to perfection. Deposited into molds. Cooled into glossy form. Wrapped in foil and paper. Sealed with purple pride. All of it designed to create one simple square that melts in your mouth. The next time you snap off a piece of dairy milk, imagine its journey. The tankers of milk rolling into the factory. The burlap sacks of Ghanaian cocoa beans pouring into roasters. The roar of rollers crushing crumb into powder. The conches rumbling like distant thunder, polishing every particle into silk. The molds vibrating, the tunnels cooling, the wrappers snapping shut. All that industry, all that precision, all that aroma condensed into a single piece of chocolate on your tongue. Maltesers begin with malt, the ingredient that gives them their unmistakable honeycomb crunch. Barley grains are soaked, sprouted, dried, and roasted long before they ever reach the factory. By the time they arrive, they're malt extract, a sticky syrup the color of dark honey, sweet and earthy with a roasted aroma. Inside the factory, massive tanks hold the extract, warm and glossy, waiting to be transformed into the airy spheres that crunch like nothing else. The first stage looks less like candy and more like baking. Flour, sugar, and powdered milk are blended with the malt extract in giant mixers, the paddles churning until the mixture forms a thick batter. The smell here is warm and bready, like fresh cereal with caramel notes. Workers lean close to test the texture. It must be smooth enough to pour, thick enough to hold air when baked. This batter is the base of every Malteser. The mixture is pumped into shallow trays and fed into ovens that stretch the length of a bus. Heat blasts across the trays, causing the malt batter to bubble and puff. Inside, steam pushes outward, creating airy pockets. By the time the trays emerge, the mixture has hardened into golden sheets that resemble honeycomb toffee. Break one open and you'd see a spongy, porous structure, light as air but strong enough to hold its shape. Those golden slabs are then crushed. Steel rollers grind them into small chunks, and vibrating sieves shake the pieces into uniform spheres. At this stage, they're pale and dusty, resembling tiny stones more than candy, but their texture is already unique, light, crisp, and almost hollow inside. These are the malt centers, the secret that makes Maltesers so addictive. The spheres travel along conveyors toward polishing drums. Massive barrels tipped on their sides that spin endlessly. Workers call them pans, and inside, the malt balls tumble over each other like pebbles in a riverbed. Here they begin their transformation into glossy chocolate orbs. Jets spray molten milk chocolate over the tumbling centers, coating them in thin layers. The process repeats again and again. Spray, tumble, dry, spray, tumble, dry. The sound inside is constant, a clatter of thousands of malt balls bouncing against metal, gradually darkening under waves of chocolate. Layer by layer, the coating builds up. The early coats soak into the porous surface, sealing every crevice. Later coats add thickness and shine, smoothing the rough edges until the balls are perfectly round. The smell is intoxicating. Roasted malt mixing with sweet, creamy chocolate, filling every corner of the room. If you peer inside the drums, you'd see a mesmerizing sight. Thousands of glossy spheres, rolling endlessly, glistening under factory lights. To finish, the Maltesers are polished. A final glaze, often made from sugar syrup or natural wax, is sprayed into the pans. As the drums spin, the glaze buffs the chocolate to a mirror-like shine. The result is iconic. Smooth, glossy spheres that rattle in your hand like marbles. It's almost hypnotic, the way dull, dusty malt centers transform into polished chocolate jewels. From here, they spill onto conveyors, rattling in rivers of chocolate orbs. Automated sorters check for perfection. Anything misshapen, cracked, or uneven is whisked away. The rest continue toward packaging, clattering in waves into funnels that portion them with exacting precision. Weighing machines drop handfuls into the signature red packets, which are sealed with a hiss of heat. Other lines feed Maltesers into sharing boxes or pouches, the packaging flying by so fast it's a blur of red and gold. Within minutes, bare malt balls have become finished candies, boxed and palletized, ready for shipping. The design of Maltesers is deceptively simple. Bite into one and you hear the snap. The airy malt crunch fracturing under your teeth. A moment later, the chocolate melts, blending with the sweet, toasted center. The contrast is deliberate. The malt is dry, light, almost brittle, while the chocolate is creamy and smooth. Together, they create a texture no other candy can replicate. Factories spend years fine-tuning the balance of malt, milk powder, and sugar to achieve that exact crunch-to-melt ratio. From the catwalks above, the factory looks like a candy storm. Drums spin endlessly, their insides rattling with thousands of rolling spheres. Conveyors shimmer with glossy chocolate orbs gliding forward in neat rows. Packaging machines snap shut with blinding speed, ejecting packets that pile into crates. The noise is relentless. The clatter of tumbling candy, the hiss of air jets, the whir of cooling fans. And over it all, the smell. Roasted malt and sweet chocolate, a fragrance that seems to hover permanently over the production floor. Durability is part of Maltesers' genius. Because the centers are so light and dry, they resist crumbling, even in bulk shipments. The chocolate shell seals them from moisture, and the glaze adds an extra barrier. That's why Maltesers can travel across oceans in shipping containers, survive months on store shelves, and still rattle perfectly when you shake the box. It's also why they're a favorite for movie snacks. Light, portable, resilient, never melting into sticky messes in your hand. The factory also produces variations. White chocolate Maltesers, where the coating pans are filled with molten ivory-colored chocolate. Dark chocolate versions, with richer, more intense shells. Some lines even experiment with flavored glazes, adding subtle caramel or honey notes. Each variation follows the same rhythm. Airy malt centers, layered in chocolate, polished to a shine, packaged in bright red or special edition wrappers. Watching the factory switch from one variety to another is like watching a magician change costumes without ever stopping the show. If you slow the process down to a single Malteser, the craftsmanship becomes obvious. A roasted malt sheet baked until golden, a sphere pressed from crumbs, light and airy. A tumble in chocolate, coat after coat, until the surface is smooth. A glaze polished to perfection, a red wrapper snapping shut, and finally, the sound of it rattling in your hand, waiting to be bitten. Multiply that by millions, and you have the factory ballet that never ends. The next time you open a packet, imagine the journey. Malt extract simmering into syrup, flour and sugar baked into golden sheets, crushed honeycomb puff spun into spheres, tumbling drums raining chocolate over thousands of centers, cooling tunnels humming with cold air, glazed polishing spheres until they shine like gems, red packets crinkling shut, crates stacking high, trucks rolling out. All of that condensed into a single bite that snaps, melts, and disappears before you realize it. Maltesers prove that lightness can be luxurious, a candy designed to be playful, rattling in your hand, vanishing in seconds, yet backed by some of the most precise engineering in the confectionery world. From malt syrup to golden honeycomb, from tumbling chocolate drums to polished spheres, they're a triumph of balance and craft. Manufacturing Almond Joy candy bars on an industrial scale begins long before any chocolate is melted or coconut is mixed. It starts with the careful sourcing and preparation of one of the candy's most iconic and defining components, the coconut. This isn't just any shredded coconut. This is a specific, moisture-balanced, finely textured variety that gives Almond Joy its distinct chewy center. Producing coconut to these specifications requires a highly controlled and deliberate process. And in modern facilities, this step alone involves extensive coordination between agricultural suppliers, food scientists, and processing engineers. The coconuts used in Almond Joy bars are primarily sourced from tropical regions like the Philippines, Indonesia, and India, where coconut palms grow in warm, humid climates and are harvested multiple times per year. The coconuts are selected based on strict criteria such as maturity, size, and oil content, all of which contribute to the flavor and structure of the final product. After harvesting, the outer husks are mechanically removed using rotary dehusking machines, exposing the inner brown shells. These shells are then cracked open using high-torque hydraulic presses or mechanical splitters, allowing access to the white coconut meat inside, also known as copra. Once separated from the shell, the coconut meat is washed in large stainless steel tanks using filtered water, sometimes with a light chlorine solution to remove any contaminants, shell fragments, or residual dirt. The clean coconut meat is then graded using high-speed rotary shredders, which reduce it into uniform strands. These industrial shredders operate at several thousand RPMs and are fitted with specialized blades designed to achieve a consistent flake size. The exact dimensions of the shredded coconut are critical. Too coarse, and the texture becomes stringy. Too fine, and it loses its chewiness. The shredded product is then passed through vibratory sieves to remove any oversized or undersized particles, ensuring each flake meets factory specifications. Once the coconut is shredded and sized, it undergoes a drying phase, designed not to fully desiccate the coconut, but to bring its moisture content into a very specific range, typically between 12 and 14%. This drying process is carried out in large belt dryers or fluidized bed dryers that blow heated air over the coconut shreds while keeping them suspended and moving, ensuring even drying throughout. Sensors embedded in the dryer constantly monitor moisture levels in real time, allowing for micro adjustments to airflow and temperature. This precision ensures that the final coconut retains its soft, moist chewiness without being wet or prone to microbial spoilage. Once dried, the coconut is cooled with ambient air and sent through a metal detection system before being packed into sterile bulk totes or drums, ready to be delivered to the candy production line. Now it's time to go into the coconut syrup blending process, where the prepped coconut is transformed into the moist, sweet filling that forms the base of every Almond Joy bar. At this stage, the dried coconut shreds are transferred from storage bins into large stainless steel ribbon blenders or planetary mixers. These mixers are food grade and designed to gently fold the ingredients together without compressing or overworking them, which would damage the texture. While the coconut is being added to the mixer, a separate part of the factory is simultaneously preparing a sugar syrup that will serve as the binder and sweetener. This sugar syrup is cooked in large steam-jacketed kettles, each fitted with agitators and temperature sensors. The syrup typically contains a blend of sucrose, corn syrup, and a small percentage of invert sugar, which helps prevent crystallization and keeps the final mixture smooth and cohesive. The ingredients are combined with water and brought to a boil, then held at a precise temperature of around 230 to 240 degrees Fahrenheit. Once the syrup reaches the desired consistency and viscosity, it is pumped through insulated transfer lines into the mixers containing the shredded coconut. The hot syrup is slowly added into the mixing chamber while the paddles rotate at a controlled speed, ensuring that every strand of coconut becomes evenly coated. This mixing step is closely monitored for torque resistance, an indirect measure of viscosity and saturation. If the mixture becomes too stiff, it indicates that not enough syrup has been added, while an overly slack consistency could suggest too much moisture. Adjustments are made in real time, either by slowing down the mixing blades or by adding additional syrup in carefully measured quantities. The end result is a glossy, dense, and aromatic coconut mixture with a smooth mouthfeel and a controlled stickiness that allows it to hold together when molded. This freshly prepared filling is discharged from the mixer into temperature-controlled holding hoppers. From there, it is fed through sanitary auger systems into the forming line, where the next phase of production begins, shaping each bar's core. But up next is the forming process, where this cohesive coconut mixture is portioned and molded into the rectangular log shape that defines the inner core of every Almond Joy. This step is handled by a specialized extrusion and forming system. The mixture is continuously extruded through a die system that determines the width and height of the log. These forming dies are custom designed for Almond Joy and produce a consistent cross-section with slightly rounded tops, ensuring a uniform bite and a reliable surface for almond placement. The extrusion head releases a continuous ribbon of coconut mixture onto a moving conveyor belt, and a high-speed rotary guillotine, timed with the conveyor's speed, cuts this ribbon into individual bar-length pieces. The distance between each cut is controlled down to the millimeter, and a sensor-based feedback system ensures that every bar is exactly the same size. After cutting, a short air blast is applied to each log to clear away any stray coconut flakes and ensure clean edges. As the bars are cut, they enter a cooling conveyor that travels through a tunnel kept at approximately 45 degrees Fahrenheit. The cooling process is essential at this point. Not only does it help the bars hold their shape, but it also stabilizes the sugar syrup binder so that the mixture doesn't slump or deform in the next step. A key consideration during this cooling stage is air humidity. If the environment is too dry, the coconut can begin to crust or dry out. Too humid, and condensation may form, which can affect downstream adhesion with the chocolate coating. For this reason, industrial humidity control units maintain relative humidity levels around 45 to 55% inside the cooling tunnel. Once cooled and firmed, the coconut logs are transferred by conveyor to the almond placement system. Each log must receive exactly 2 whole almonds, neither more nor less, positioned evenly across the top surface. The almonds used in this process are themselves the result of a careful preparation sequence. Raw almonds are sourced from large-scale growers, often in California, and are received at the factory in bulk containers. These almonds are sorted, cleaned, and then dry roasted in large convection ovens. Roasting enhances flavor, reduces moisture to less than 5%, and gives the almonds the crunch consumers expect. After roasting, the almonds are cooled and transported to a hopper above the placement system. Here, they are singulated, separated into single file, and guided into individual almond placement arms. These arms are controlled by a vision-guided robotic system that tracks the position of every coconut log in real time. Using photoelectric sensors and high-resolution cameras, the system places each almond with millimeter-level accuracy on top of the log. The almonds are pressed into the surface just enough to adhere without sinking, and an inline inspection system checks that every bar has precisely 2 almonds aligned correctly. Any bar that deviates from this standard is removed from the line for manual inspection or rework. Now it's time to go into the chocolate enrobing stage, which marks the beginning of the transformation from a basic assembly of ingredients into the finished, glossy, consumer-ready candy bar. This process involves fully coating the almond-topped coconut cores with a layer of milk chocolate. But this is no ordinary chocolate. It has been specifically formulated and tempered to provide the right snap, shine, and melt-in-the-mouth texture that defines the almond joy eating experience. The chocolate is stored in holding tanks maintained at 110 to 115 degrees Fahrenheit and stirred continuously to ensure it remains fluid and free from separation. Before use, the chocolate is tempered through a process that heats, cools, and reheats it to align the cocoa butter crystals in a stable form. Proper tempering is essential as it prevents fat bloom and gives the coating its glossy finish and clean break. The tempered chocolate is pumped into an enrobing machine, which dispenses it in a continuous curtain across the width of the conveyor belt. As the coconut and almond cores pass underneath, they are fully submerged in the falling sheet of chocolate, while a bottoming unit applies a layer of chocolate to their underside. Immediately afterward, a series of air blowers remove excess chocolate, ensuring a uniform thickness and revealing the shape of the almonds beneath. What emerges is a fully coated bar that looks and feels like the final product, but still needs time to set. That step begins as the bars enter a temperature-controlled cooling tunnel, and that's where the next phase begins. Inside the cooling tunnel, a meticulously engineered, climate-controlled chamber extending over 30 feet in length, the freshly enrobed Almond Joy bars begin their chocolate setting phase. This tunnel is one of the most crucial parts of the process, ensuring that the tempered chocolate coating transitions from a glossy liquid into a solid shell with the perfect texture and finish. The chocolate must cool at a precise rate, not too fast, which could result in cracking or sugar bloom, and not too slowly, which could cause the cocoa butter crystals to misalign, leading to dullness or fat bloom on the surface. The tunnel operates at an ambient temperature between 45 and 55 degrees Fahrenheit, and relative humidity is tightly controlled around 50%. High-efficiency fans circulate cold air evenly across all bars on the conveyor, and temperature sensors track minute variations along the length of the tunnel. The speed of the conveyor is carefully synchronized with the chocolate's crystallization curve so that the bars spend just the right amount of time cooling, usually between 7 and 12 minutes, depending on environmental conditions, line speed, and chocolate thickness. During this stage, the chocolate coating fully hardens around the coconut and almond core, creating a glossy, smooth outer layer that locks in moisture and flavor. The almonds, having been gently pressed into the top of the coconut before enrobing, remain clearly visible through the chocolate shell, creating the bar's iconic bumpy silhouette. As the bars exit the tunnel, they are now fully formed, with all primary ingredients integrated and stabilized. But the next phase, inspection and quality control, ensures that only perfect bars make it into the hands of consumers. The next step is the multi-layered inspection and quality assurance phase, a critical junction in the Almond Joy manufacturing process. Here, each fully cooled, enrobed bar passes under a series of digital scanning systems equipped with high-resolution cameras and sensors that detect inconsistencies in shape, size, and appearance. These systems analyze every bar in real time using image recognition algorithms trained to identify surface defects, incomplete chocolate coverage, missing almonds, or any signs of misalignment. Each camera system captures dozens of images per second, creating a detailed digital fingerprint of each bar. If a defect is detected, such as an air bubble on the surface, a chocolate smear, or a misaligned almond, the bar is automatically rejected using a quick puff of compressed air that directs it off the main conveyor into a designated collection tray. Rejected bars are recorded and analyzed in quality control logs to monitor trends and flag any upstream issues in real time, like syrup inconsistencies or almond placement variances. Following the visual inspection, the bars pass through an inline check weighing station. This precision balance system measures the mass of each individual bar down to the 1/10 of a gram. Bars that are even slightly under or overweight are flagged and rejected from the line. This strict weight control not only ensures product consistency and consumer satisfaction, but also regulatory compliance, as all packaged goods must meet labeled net weight declarations. These check weighers are recalibrated frequently during production to maintain absolute accuracy, and the results are logged digitally to provide traceable batch records. Next, a random sampling process is initiated where trained human inspectors pull sample bars from the line every few minutes. These samples are taken to a nearby quality assurance room for deeper evaluation. Inspectors slice open the bars and examine the cross-section for proper ingredient distribution, moisture retention in the coconut layer, almond placement, and shell integrity. Taste testing is performed by a trained sensory panel in a separate tasting room to ensure the flavor profile remains consistent. Parameters like sweetness, chewiness, and chocolate snap are all evaluated and recorded in a detailed quality report. Once bars have successfully passed through the inspection phase, they are ready for the next stage, packaging. But up next is the flow wrapping process, where each Almond Joy bar is individually wrapped using high-speed machinery designed to maintain hygiene, preserve freshness, and uphold branding consistency. The packaging film, pre-printed with the Almond Joy logo and product information, is loaded in giant rolls at the start of the packaging line. These rolls are threaded through a series of rollers and tensioners that keep the film aligned and taut as it's fed into the wrapping unit. The bars are spaced and synchronized onto a conveyor lane and fed into the flow wrapping machine, which envelopes each one in film and seals it at the sides and ends using heated crimping jaws. These jaws press the film together and apply controlled heat and pressure to create airtight seals that are strong yet easy to open. The sealing temperatures are carefully monitored to avoid overheating the chocolate within, as excess heat could cause the surface to dull or soften. Each wrapped bar is then passed under a thermal inkjet or laser coder, which prints the best before date, batch code, and production time directly onto the wrapper. This traceability information is vital in case of recalls, inventory tracking, or shelf life analysis. Vision sensors verify the presence and clarity of the code, and any missing or illegible codes trigger a rejection mechanism. The speed of this entire process is remarkable. Modern flow wrappers can handle upwards of 500 bars per minute, all synchronized perfectly to match the upstream enrobing output. Once wrapped and coded, the Almond Joy bars are grouped into retail-ready formats. Depending on the destination, this could mean twin packs, king-size versions, or standard singles in cartons. Cartoning machines fold and glue cardboard sleeves or cartons, then insert the correct number of bars automatically. These cartons are scanned for correct orientation, closed, and labeled with shipping and SKU data. A final check weigher ensures that the total weight of each carton falls within specification, and the completed units are then moved down the line to case packing. The case packing phase involves automated robotic arms or pick-and-place systems that lift finished cartons and place them into larger, corrugated shipping cases. The arrangement within each case is optimized for pallet stability and protection during transit. Each case is labeled with product identifiers, batch codes, and destination information, then sealed and conveyed to a palletizing station. Palletizing robots stack the cases onto wooden or plastic pallets in precise configurations to maximize space and maintain structural integrity during transport. Once a full pallet is assembled, it's wrapped in high tensile stretch film using automated rotary arm or turntable wrappers. This wrapping secures the load against shifting during transportation and also provides a barrier against dust and moisture. Each pallet is then tagged with a barcoded shipping label that includes tracking information, weight, and customer-specific handling instructions. The completed pallets are moved to a climate-controlled storage area within the warehouse to await shipment. Now, it's time to go into the logistics and distribution stage, where the focus shifts from production to coordinated movement and inventory management. Almond Joy bars, like all Hershey's products, are managed within an enterprise resource planning system that tracks production batches, inventory turnover, and customer orders in real time. Based on demand forecasts, pallets are selected for outbound shipment, assigned to specific trucks or containers, and scanned out of the warehouse with full digital traceability. Transport is typically handled using refrigerated trucks during warmer months, as the milk chocolate in Almond Joy bars is sensitive to heat. Temperatures are maintained between 55 and 65 degrees Fahrenheit during transit, and GPS-linked thermal loggers monitor each vehicle's internal climate from origin to delivery. If a truck deviates from its safe range, alerts are sent to both logistics managers and warehouse supervisors to prevent spoilage. Once the bars reach regional distribution centers or retail warehouses, the product is scanned into inventory and routed to store shelves. Retail partners rely on synchronized inventory systems that replenish stock as it sells, often based on point-of-sale data. The entire journey, from Coconut Grove to grocery store, can be completed in just a matter of weeks, but every phase must function flawlessly to deliver a bar that meets Hershey's standards for quality, freshness, and consistency. And even once the product hits shelves, the factory's job isn't done. Ongoing consumer feedback, seasonal demand changes, and promotional cycles influence continuous adjustments in batch sizes, production schedules, and packaging variations. Special holiday versions, multi-packs, and limited time offers are all planned months in advance and require tailored processes, new molds, and reprogrammed machinery, an impressive level of flexibility embedded within an otherwise standardized production system. Quality assurance continues to play an active, ongoing role in the manufacturing of Almond Joy, even after the bars have been wrapped, packed, and prepared for distribution. In fact, behind the scenes of the main production line, a parallel infrastructure operates continuously to monitor, record, and validate every element of the process in real time and long after the initial production phase. This includes not only in-process checks, but detailed post-production sampling and retention, which are central to traceability, regulatory compliance, and product consistency. One critical ongoing practice is the archiving of batch samples. As bars are wrapped and prepared for shipment, dedicated staff routinely pull random samples from each batch, often one every few thousand bars. These samples are sealed, labeled, and logged with all relevant metadata: the exact time of production, line number, raw material codes, chocolate viscosity at time of enrobing, coconut moisture content, and even almond roast profiles. These reference bars are stored in secure, climate-controlled storage units maintained at conditions that mimic ideal shelf environments. The goal is to preserve these products in a stable state for up to 2 years, during which time they may be retrieved for comparison if any quality concerns or deviations arise. In addition to acting as an insurance policy against customer complaints or distributor queries, these archived samples are regularly tested as part of long-term shelf life studies. Trained quality assurance technicians perform controlled aging studies by artificially accelerating the aging process in heated chambers to evaluate how the product will hold up over time. These studies track changes in coconut chewiness, chocolate bloom resistance, almond crunch retention, and overall flavor integrity. Sensory analysis is conducted by expert panels who evaluate sweetness, aroma, textural contrast, and mouthfeel using standardized scoring systems. This data feeds back into ingredient sourcing decisions and packaging refinements, allowing the team to adjust variables well before any potential issues could reach consumers. Now, it's time to go into the digital control systems that operate silently beneath every piece of equipment, coordinating, recording, and adjusting every stage of the Almond Joy production process. At the core of this system is a network of programmable logic controllers, PLCs, which manage the real-time operation of machinery across the factory floor. These industrial computers are programmed to respond to sensor inputs and control outputs with extreme precision, enabling the synchronization of critical events such as syrup dosing, coconut extrusion, chocolate tempering, and wrapper sealing. For example, if the syrup temperature in the blending kettle falls even slightly below the optimal range of 235 to 240 degrees Fahrenheit, the PLC will automatically trigger a compensatory adjustment in steam pressure. Similarly, if a sensor detects that the chocolate curtain in the enrober has begun to thin, indicating an issue with flow rate or chocolate viscosity, the system can alter pump speed, activate an agitator, or send an alert to the line technician. These reactions happen in milliseconds, ensuring seamless operation with minimal human intervention. All this data funnels into a supervisory control and data acquisition system, or SCADA, which acts as the digital nervous system of the plant. SCADA systems provide centralized visualization of every variable in production, from torque readings in the coconut mixes to conveyor belt speeds on the packaging line. Live dashboards display real-time metrics alongside historical trends, and operators can set control limits to trigger alarms, shutoffs, or automatic corrective actions when deviations occur. Data logging is continuous, with every action time-stamped and stored in redundant backups for audit and analytics purposes. But up next is the role of continuous improvement teams and how they use this wealth of production data to fine-tune the manufacturing process. Rather than viewing each shift as a discrete operation, modern Almond Joy factories treat every minute of production as a learning opportunity. Statistical process control specialists and lean manufacturing engineers analyze massive volumes of data to identify small but significant trends. For instance, if there's a subtle uptick in the rate of chocolate flow variation on line 2 during evening shifts, it might suggest thermal drift in the tempering unit or minor calibration errors in the chocolate pump. These insights allow preventive maintenance schedules to be updated, saving time and resources while minimizing the risk of future disruptions. Some adjustments are made on the spot, while others lead to full pilot testing cycles. Pilot lines, scaled-down versions of the full production setup, allow engineers to test adjustments to temperature profiles, mixing durations, or conveyor speeds without interrupting primary operations. For example, if a new batch of coconut arrives with slightly higher fat content than normal, the pilot team may experiment with modified syrup ratios or mixing times to maintain the same moisture binding characteristics. Results are measured using laboratory tools like refractometers, rheometers, and moisture analyzers. And the most successful configuration is then rolled out to full production. The focus on fine-tuning doesn't stop at equipment and ingredients. It also extends to the behavior of the product throughout the supply chain. Some Almond Joy bars are shipped across the country or even internationally, and that means packaging and formulation must perform under a wide range of conditions. Engineers perform transit simulations using vibration tables and thermal chambers to replicate the effects of long-distance trucking or air freight. These simulations allow packaging specialists to evaluate wrapper integrity, seal strength, and chocolate stability under heat and motion stress. In cases where performance can be improved, new materials or layering structures are proposed, often months before the consumer ever sees the final package. Toblerone chocolate production begins with the sourcing and intake of its core raw materials: cocoa mass, cocoa butter, sugar, milk powder, honey, almonds, and soy lecithin as an emulsifier. The distinct taste of Toblerone, known for its smooth Swiss milk chocolate interspersed with chewy nougat and honey almond notes, relies on both the precision of ingredient handling and the consistency of every preparation stage. The factory intake process starts with the arrival of these ingredients at the manufacturing plant's loading bay. Each ingredient is stored and transported under specific conditions tailored to its nature. For example, cocoa mass and cocoa butter, which are highly sensitive to temperature and oxidation, are delivered in thermally stabilized containers that keep them in a semi-solid state. Upon arrival, these containers are immediately transferred into insulated storage tanks inside the facility to prevent exposure to ambient air and humidity. These tanks are purged with inert nitrogen gas to minimize oxidation and preserve flavor integrity. Milk powder, sugar, and lecithin arrive in sealed food-grade sacks or large bulk bins and are lifted by pneumatic suction systems into silo units for temporary storage. Before anything enters the production stream, comprehensive quality assurance testing is conducted. Samples from each delivery are checked for microbiological safety, color, flavor, moisture content, and texture. Specialized equipment such as near-infrared spectrometers and rotary viscometers are used to assess these parameters in real time. Once verified, the production of the chocolate base begins. This base, which will serve as the core medium for all Toblerone bars, is created by combining cocoa mass, cocoa butter, sugar, and milk powder. Each of these components is dispensed into high-capacity stainless steel mixers in precise ratios dictated by the Toblerone formulation. These mixers are automated and fitted with load cells to ensure that each ingredient is weighed to the gram before being introduced to the blend. The contents are mixed at low speed to ensure a homogeneous distribution of particles without excessive aeration. This preliminary mixture, however, is far from the final silky chocolate. At this stage, the texture is coarse and grainy. To refine it, the mix is fed into a 5-roll refiner. The 5-roll refiner is a massive piece of machinery consisting of 5 horizontally aligned steel rollers that compress and shear the chocolate particles down to a size between 18 and 25 microns. This reduction in particle size is critical for mouthfeel. If particles remain larger than 30 microns, the human tongue perceives a gritty texture. Below 20 microns, the chocolate begins to melt smoothly and luxuriously in the mouth. During refining, sensors continuously monitor the gap between rollers and particle fineness using real-time laser diffraction analysis. Excessive refining can result in overheating or fat separation, so the temperature of each roller is actively cooled and monitored to maintain uniform conditions. The refined paste exits the refiner as a silky, thick, and slightly warm material, ready for the next stage, conching. Conching is the step where Toblerone's flavor is truly developed and its texture perfected. The conche machine is a large enclosed vessel that contains mechanical arms or rotors that knead the chocolate mass for several hours. This process serves multiple purposes. First, it evaporates unwanted volatile compounds, such as acetic acid or aldehydes, that may have formed during roasting or refining. Second, it distributes the cocoa butter evenly around each solid particle, coating them thoroughly and improving the overall flow behavior of the chocolate. The conching process typically lasts between 6 and 12 hours, depending on the batch size and the desired profile of the chocolate. During this time, emulsifiers such as soy lecithin are added to reduce the chocolate's viscosity without increasing the fat content. This makes the chocolate easier to mold and coat, while also enhancing its melt-in-the-mouth properties. It is also during conching that the iconic honey and nougat flavor notes of Toblerone begin to be layered in. Honey is added in measured amounts, not just for sweetness, but also to contribute to the product's distinct aroma and chewiness once combined with nougat. The factory conching process uses controlled heat, usually between 45 degrees Celsius and 80 degrees Celsius, to keep the cocoa butter in a liquid state. Temperature control is crucial. Too hot, and the chocolate risks burning or developing off flavors. Too cold, and the process slows, failing to drive off sufficient moisture. Modern conches are equipped with real-time pH, moisture, and volatile compound sensors that feed back into the control system, allowing operators to adjust mixing speed, arm pressure, or temperature on the fly. Once the conching is complete, the resulting chocolate is an ultra-smooth, shiny, and aromatic mixture. It is pumped into jacketed holding tanks that keep it at a stable temperature of around 30 to 32 degrees Celsius, ideal for downstream processes such as tempering and molding. These tanks are constantly agitated to prevent fat separation and crystallization. The next stage, tempering, is a pivotal process that controls the crystal structure of cocoa butter in the chocolate. Cocoa butter can crystallize in several different forms, but only one form, Form V, produces chocolate that is glossy, firm, and resistant to melting at room temperature. Achieving this form requires carefully heating and cooling the chocolate through a specific temperature curve. Tempering is done in continuous tempering machines where chocolate is first heated to around 45 degrees Celsius to eliminate all previous crystal formations, then cooled down to approximately 27 degrees Celsius to initiate the formation of stable seed crystals. The chocolate is then gently reheated to around 31 to 32 degrees Celsius to eliminate any unstable forms and maintain only the desired crystalline structure. These temperature transitions are tightly controlled by heat exchangers and thermal sensors, which ensure that the flow and crystallization kinetics of the chocolate are kept within narrow limits. With the tempered chocolate now perfectly conditioned and held at its ideal working temperature, it's time to move into one of the most distinctive and meticulously engineered steps of the entire Toblerone production process: molding the chocolate into its iconic triangular bar shape. This is not simply about pouring chocolate into a unique mold. It involves a detailed and highly synchronized series of movements designed to maintain structural integrity, precision alignment, and uniformity across millions of units. The Toblerone mold consists of a series of equidistant triangular cavities arranged in a straight line. Each mold cavity is designed to hold a single triangle of the bar, with narrow necks between them that allow for precise chocolate flow while ensuring each triangle remains individually defined yet conjoined. These molds are made of food-safe, high-strength polycarbonate and are preheated to prevent premature cooling when the liquid chocolate is deposited. Preheating ensures the chocolate flows evenly into every corner of the mold without setting too quickly, which could cause defects like air bubbles or incomplete shapes. Before chocolate enters the mold, the entire cavity array is vibrated at a high frequency using a precision-controlled shaker system. This vibration helps eliminate trapped air, allowing the chocolate to settle smoothly and evenly. The vibrating stage is calibrated to match the viscosity of the chocolate in real time, using inline sensors that monitor the chocolate's flow behavior. Any slight deviation in viscosity can affect how well the chocolate fills the narrow base points of the triangular molds, so the system adjusts shaker speed accordingly. Once the molds are filled, they pass under a leveling scraper to ensure the chocolate surface is perfectly flat along the bottom of the bar, which will ultimately become the base. A second, shorter vibration cycle occurs after this to further consolidate the chocolate and ensure all suspended particles, especially small bits of nougat or almonds, are evenly dispersed within each triangle. If the nougat or honey pieces were to settle unevenly during this stage, it would create inconsistent textures and affect quality. At this point, the filled molds are slowly moved into a multi-zone cooling tunnel. The tunnel is designed to gradually reduce the temperature of the chocolate from around 32 degrees Celsius to below 10 degrees Celsius over the course of several minutes. The zones begin with gentle ambient cooling, progressing through stages of increasingly chilled air, circulated by high-efficiency fans. The slow drop in temperature is crucial. If chocolate is cooled too rapidly, it can develop stress fractures, surface bloom, or uneven crystallization. The cooling system is monitored constantly using digital thermometers, hygrometers, and flow sensors to guarantee uniform airflow and humidity across every inch of the tunnel. As the molded bars pass through each zone, the cocoa butter crystallizes uniformly into the stable Form V lattice structure, locking in glossiness and snap. This stage also causes the chocolate to shrink slightly away from the walls of the mold, which facilitates easy demolding later. Once the bars exit the cooling tunnel, they are still within the molds, but now fully solidified and dimensionally stable. Next, the demolding process begins. The molds are inverted onto conveyor belts equipped with soft silicone pads that cushion the fall of each bar as it's ejected. Demolding can be done either pneumatically, where jets of compressed air push the back of the mold to dislodge the bar, or mechanically, using plungers that gently press the chocolate out. In either case, sensors monitor the success rate of ejection, and any mold that fails to release the bar is automatically sent to a rework line. Once the Toblerone bars are released from the molds, they are briefly passed through an inspection station where machine vision systems check for mold, fill consistency, breakage, surface defects, and geometric conformity. High-resolution cameras and laser profiling tools compare each bar against stored 3D models. Bars that fall outside tolerance thresholds are marked for reprocessing, where they will be remelted and reintegrated into the production line. The successfully molded and cooled bars now enter the next phase, packaging. Before wrapping, each bar passes through a controlled dehumidification tunnel. This step is critical for preventing condensation during packaging, which could lead to microbial growth, sugar bloom, or spoilage. The dehumidifier maintains an environment below 30% relative humidity and gently warms the air around the chocolate to just above ambient temperature, allowing any moisture on the surface to evaporate without melting the chocolate. Once surface conditions are stabilized, the Toblerone bars move to the wrapping station. Here, the bars are individually picked and aligned onto a high-speed belt, where the characteristic triangular cardboard sleeve is automatically wrapped around each one. The sleeves are die-cut from pre-printed cardboard stock, folded precisely, and glued using food-safe adhesive. Each wrap is barcoded and batch-coded in real time, using inkjet printers synchronized with the production software. After the sleeve is applied, some product variations receive a foil wrapping beneath the cardboard. The foil is cut from gold-colored rolls and folded tightly around the chocolate by robotic arms using pre-programmed pressure patterns that ensure coverage without crushing the delicate points of the triangles. The foil serves as an oxygen and light barrier to prolong shelf life, especially for Toblerone products destined for warmer climates or long export journeys. Every wrapped bar is now scanned and weighed by automated inspection stations. Any unit that falls below or exceeds target weight, accounting for chocolate and packaging, is removed from the line for manual inspection. Those that pass all checks are sorted into bundles depending on product format: single bars, multi-packs, or gift sets. The bars are grouped into cartons by pick-and-place robots. These robots use suction cups and soft grippers to avoid damaging the points of the chocolate triangles. The cartons are then sealed, labeled with lot and traceability data, and stacked into master cases. Each master case is assigned a tracking code and loaded onto pallets using robotic palletizers programmed for maximum cube efficiency and stability. These pallets are then wrapped with stretch film and stored in temperature-controlled warehouses. Warehouse conditions are kept between 16 degrees Celsius and 18 degrees Celsius, with less than 50% humidity to prevent bloom and preserve texture. Pallets are logged into a central warehouse management system that coordinates batch rotation using FIFO principles, ensuring freshness upon delivery. Now that the Toblerone bars have been successfully molded, inspected, and packaged into their iconic triangular sleeves, the next stages of the factory operation transition from chocolate engineering into full-scale logistics, global adaptation, and product diversification, all of which require just as much planning, precision, and technical orchestration as the earlier phases of the chocolate creation itself. The journey from packaged bar to store shelf begins in the factory's outbound logistics area, where every finished pallet is scanned into the warehouse management system. The system integrates with enterprise resource planning software to track inventory levels, prioritize shipping based on destination climate, customs requirements, and expiration dates, and coordinate loading dock activity to maximize efficiency and avoid bottlenecks. At this point, temperature control becomes a dominant concern. Because chocolate is sensitive to thermal shock and prolonged exposure to high humidity or temperatures, all shipments are required to pass through insulated loading bays equipped with temperature buffering systems. These systems maintain consistent conditions even as trucks are loaded, preventing any temporary environmental spikes that might affect product integrity. For shipments destined for nearby distribution centers within a 200-kilometer radius, standard refrigerated trucks are used. These trucks are pre-cooled to the exact storage requirements, typically 16 to 18 degrees Celsius, and each one is fitted with temperature loggers and GPS tracking units that upload data to the central logistics server in real time. Any deviation in internal truck temperature during transit is flagged automatically, prompting quality control checks upon arrival. For export shipments, particularly to regions like Southeast Asia, Africa, or South America, Toblerone products are loaded into refrigerated shipping containers with independent power units, ensuring continuous cold chain conditions during ocean transport that may span up to 3 weeks. Each pallet is labeled with multiple identifiers, including product code, lot number, production time, line number, and temperature certification. These labels are printed using thermal transfer printers that embed RFID chips or scannable QR codes to allow full traceability. This level of detail is critical not only for internal logistics and recall management, but also to meet the regulatory requirements of import authorities in different countries. For instance, Gulf countries may require halal certification to be attached to the consignment, while Japan may demand documentation showing compliance with their unique food additive regulations. Toblerone's global logistics strategy is thus heavily embedded in regulatory compliance, with dedicated teams managing certification, customs documentation, and export logistics. Back within the facility, the production line doesn't operate in isolation. It's part of a broader, synchronized network of production scheduling. Toblerone is not produced as a single SKU, but in a wide variety of formats, each requiring slightly different processing configurations. These include the classic 100-gram bar, 50-gram snack bar, 360-gram gifting box, tiny 12.5-gram miniature pyramids, and specialty editions like white chocolate or dark chocolate variations. Each variation has a specific recipe profile, mold configuration, cooling requirement, and packaging format. Switching between variants requires a carefully managed process known as a changeover. A changeover begins with a complete emptying of all hoppers, pipelines, and depositors currently filled with one chocolate variant. The equipment is flushed using tempered cocoa butter or neutral chocolate mass to clear residual flavors and prevent cross-contamination. Then, the line undergoes a clean-in-place cycle involving detergent wash, water rinse, and final steam sanitization. Sensors measure residual proteins and fats in rinse water to confirm cleanliness. Only after quality control confirms a clean system does the new variant's ingredients enter the production stream. Changeovers also affect the molding system. For example, miniature Toblerone shapes are molded using smaller polycarbonate trays that are swapped in with robotic carriage systems. These molds pass through the same preheating, filling, vibration, and cooling steps as their larger counterparts, but on accelerated cycles due to their reduced volume and mass. The packaging system, too, must adapt. Larger bars require stronger folding cartons with inner trays, while minis are often flow-wrapped and placed into pouches or mixed assortment boxes. To handle this, the line includes modular packaging equipment that can be reprogrammed within minutes using preset SKU profiles. Operators scan a barcode for the new SKU, and all conveyor speeds, arm timing, and print data update automatically. A parallel stream of work takes place in Toblerone's research and development lab, often co-located with the factory or within the company's broader innovation campus. Here, food technologists and process engineers develop new flavor profiles, test alternative sweeteners, and design special edition runs tailored to holidays, partnerships, or regional taste preferences. For example, a limited edition bar infused with salted caramel may require different sugar crystallization controls, or a Ramadan edition might include date extract and modified packaging with Arabic text. Pilot-scale batches are created on miniaturized versions of the factory equipment, allowing experimentation without interrupting commercial-scale output. Every new recipe that graduates from R&D to factory production goes through a phase called scale-up validation. During this stage, the formulation is first made on a semi-commercial line capable of producing thousands of units per hour, and multiple parameters are tested: ingredient behavior under continuous agitation, flow characteristics during tempering, molding fidelity in standard production molds, and thermal stability during cooling. If the results meet the product development benchmarks, full-scale production is approved. Another important dimension of Toblerone's operation is environmental stewardship and factory sustainability. In recent years, the facility has upgraded many of its core systems to reduce carbon footprint, minimize waste, and improve energy efficiency. The chocolate tempering machines now utilize closed-loop thermal exchange systems that recycle cooling energy from one process to another. The air handling systems in the cooling tunnels and clean rooms have been upgraded to variable speed drives and high-efficiency particulate air filtration, significantly cutting energy usage while maintaining product safety. In terms of ingredient sustainability, Toblerone's cocoa is sourced under certified ethical sourcing programs, which ensure that the farms supplying cocoa beans are paid fairly, do not use child labor, and implement agroforestry practices that support biodiversity. These cocoa beans are processed into cocoa mass and cocoa butter by contract processors who follow Toblerone's strict quality and sustainability protocols, including traceability from farm to factory. The almonds and honey, too, are held to exacting standards. Almonds are supplied by certified orchards in California or the Mediterranean, sorted for size and oil content. Honey is sourced with attention to floral origin, ensuring a consistent flavor batch after batch. In-house testing includes pollen analysis, sugar spectrum fingerprinting, and moisture checks. This commitment to sourcing excellence reinforces the brand's identity as a premium Swiss chocolate. Finally, consumer safety and food compliance are at the core of every step of the Toblerone factory. All areas of the facility are subject to strict zoning protocols, separating raw ingredient handling from finished product areas to prevent contamination. Staff undergo regular hygiene training, wear full protective clothing, and enter through sanitation airlocks that include hand washing, boot scrubbing, and compressed air garment cleaning. Equipment is built to hygienic design standards, with no exposed threads, crevices, or moisture traps. Quality assurance checkpoints occur at dozens of locations throughout the line. Metal detectors are installed post-packaging to catch any foreign material. Check weighers ensure that each unit falls within exact mass tolerances. Barcode scanners verify packaging accuracy. And final batch records are signed off by a trained quality technician before any shipment is released. Even the slightest anomaly, an over-tempered batch, a slightly tilted mold, a misaligned wrapper, is caught, logged, and addressed through a root cause analysis process. Every detail matters because Toblerone is not simply a chocolate bar. It's a global symbol of quality, tradition, and precision engineering. What looks like a single, satisfying triangle is actually the result of hundreds of synchronized decisions, operations, and technologies that function in harmony to deliver an unchanging standard of excellence. With the full-scale production, molding, packaging, and international logistics already finely tuned, the final stages of Toblerone's manufacturing process revolve around final distribution, continuous improvement protocols, consumer-facing customization, and digital integration that modernizes how quality and efficiency are sustained across an ever-growing global demand. Once pallets of finished, labeled, and verified Toblerone products are ready for shipment, they enter the outbound logistics management system, where real-time data on shipping routes, order queues, and warehouse availability determine where each batch goes next. The system doesn't just track inventory, it optimizes routes based on transportation cost, shelf life preservation, retail replenishment cycles, and sales forecasts provided by global distribution partners. Whether a shipment is bound for a Swiss airport duty-free zone, a North American grocery chain, or an e-commerce fulfillment center, its path is selected based on minimizing transit time and maintaining perfect storage conditions. Each truck or container that leaves the factory is accompanied by digital and printed documentation that includes compliance declarations, temperature logs, ingredient traceability records, and destination-specific export certificates. These are often required at borders for customs clearance. particularly in markets with strict regulations around food labeling, allergens, or religious dietary requirements like halal or kosher certifications. The factory's compliance team works in sync with shipping personnel, constantly updating their records as international regulations evolve. Inside the production facility itself, continuous improvement is embedded at every level. Daily performance metrics are posted on digital displays throughout the production floor, tracking everything from machine uptime and output per hour to defect rates, waste percentages, and energy usage. Operators have access to touch panel controls that allow them to report faults or initiate adjustments on the fly. When an anomaly is detected, it's logged in a root cause tracking system that prompts follow-up from engineering or quality assurance teams. This immediate feedback loop is designed to prevent small issues from becoming systemic problems. Preventive maintenance also plays a major role in sustaining Toblerone's high production standards. Every piece of equipment in the line, from chocolate mixers to automated packers, is tagged with a maintenance schedule integrated into the plant's CMMS. Operators are prompted automatically when a belt needs replacement, a blade needs sharpening, or a motor requires lubrication. By minimizing unplanned downtime, the factory ensures consistency in output and avoids any deviation from scheduled production volumes. Consumer customization is another frontier in Toblerone's manufacturing strategy. For promotional seasons, corporate gifting campaigns, or regional celebrations, Toblerone offers limited edition bars with printed names, holiday messages, or even national flag motifs. Chocolate begins its life not in the factory, but on the tropical cacao farms that line the equator. These farms are located in countries across West Africa, Central and South America, and Southeast Asia, with Ivory Coast and Ghana among the world's top producers. The climate in these regions, hot, humid, and with rich, well-draining soil, is essential for the cultivation of Theobroma cacao, the tree that produces cacao pods. Each pod contains 20 to 50 seeds, known as cacao beans, surrounded by a sweet, pulpy, white fruit. These beans are the raw foundation of all chocolate products. The cacao harvest is entirely manual. Farmers use machetes or curved knives attached to long poles to carefully cut ripe pods from the trees without damaging the branches. A single mature tree may produce between 20 and 30 pods per year, and since cacao does not ripen all at once, harvesting occurs continuously over several months. Once harvested, the pods are collected in piles and opened by hand using machetes. The beans, still coated in sticky white pulp, are scooped out and prepared for fermentation, the first transformative step in the chocolate making process. Fermentation typically occurs on the farm or at centralized collection centers. Though it might sound like a simple resting period, fermentation is a critical and highly sensitive step that chemically alters the beans and begins to develop the flavor precursors of chocolate. Beans are placed in shallow, slatted wooden boxes or piled into heaps and covered with banana leaves. This environment encourages the growth of natural yeasts and bacteria that convert sugars in the pulp into alcohol and acids. As the temperature rises, often reaching 45 to 50 degrees Celsius, the bean's internal structure changes. Enzymes are activated, cell walls are broken down, and bitter polyphenols begin to transform into the complex flavor compounds that will later give chocolate its signature taste. Fermentation typically lasts 5 to 7 days, during which the beans are turned or mixed once or twice a day to ensure even microbial activity and oxygenation. This step is closely monitored, as under-fermentation leads to bland or vegetal flavors, while over-fermentation can introduce off notes like mold, vinegar, or excessive bitterness. Many large chocolate manufacturers, even though they don't ferment beans on site, have established quality programs with their cacao suppliers, training them in fermentation control, and even requiring on-site testing of pH and temperature during the process. Once fermentation is complete, the beans are spread out to dry. Drying can be done on large tarpaulins, bamboo mats, or raised wooden platforms under the sun. Industrial cacao processors often prefer sun drying, which can take 5 to 10 days, as it produces cleaner, more natural flavor profiles. During drying, the beans are turned regularly to ensure even moisture loss. The goal is to reduce the moisture content to around 6%, 7%, a safe level that prevents mold and microbial growth during storage and transport. At this point, the beans are still covered in their thin, brittle shells and have taken on a dark brown color, with their signature earthy, chocolatey aroma starting to develop. The beans are carefully bagged in burlap sacks, usually 60 to 65 kilograms per bag, and labeled with origin information including country, region, farm or co-op, and processing dates. These bags are then consolidated for export. Exporting cacao beans requires extreme care and logistics planning. Moisture, heat, and exposure to foreign odors can degrade the beans before they even reach the factory. To prevent spoilage, the sacks are loaded into dry, ventilated shipping containers, often lined with insulating material or desiccant packs to control humidity. During long overseas shipments, particularly by sea freight, the cargo is monitored using data loggers that track temperature and humidity. If the beans are exposed to extreme conditions, entire shipments can be rejected by the receiving chocolate manufacturer. When the beans arrive at the chocolate factory, usually located in Europe, North America, or Asia, they undergo a rigorous intake and inspection process. This is where industrial chocolate production truly begins. First, the bags are unloaded into a receiving area, where samples are drawn from each lot and taken to the quality control lab. Here, technicians measure moisture content, check for mold or insect damage, and grade the beans based on size, color, and cut tests. Cut tests involve slicing a sample of beans lengthwise and examining the cross-section. Properly fermented beans will have a uniform, slightly purplish interior with no signs of germination or off colors. Beans that meet the manufacturer's standards are then approved for processing. The sacks are emptied into large hoppers that feed the cleaning and pre-processing line. At this point, the factory begins to function much like a grain mill, sorting, cleaning, and prepping the raw material for transformation. The first stage is mechanical cleaning. The beans pass through vibrating screens and air jets that remove sticks, stones, dust, string, and other foreign materials. Magnetic separators remove any stray metal particles picked up during harvest or shipping. After cleaning, the beans are often sorted by size. This is an optional step, but many high-end chocolate makers insist on sorting to ensure that beans of uniform size are roasted together. Uneven roasting is a major risk if large and small beans are mixed, as the small beans may burn while the larger ones under-roast. Before roasting, the factory may also conduct a dehumidification step, particularly if the beans arrived slightly above target moisture. Large rotary dryers or low-temperature ovens are used to bring the beans into precise moisture range, often 5%, 6%, to prepare for optimal roast conditions. This is all monitored through programmable logic controllers that track time, temperature, airflow rate, and moisture loss in real time. With the cacao beans now thoroughly cleaned, dried to precise moisture levels, sorted by size, and passed through rigorous quality inspections, the chocolate production process enters one of its most transformative and delicate phases: roasting. This step marks the moment when raw agricultural product begins to develop the hallmark sensory properties of finished chocolate: aroma, depth, bitterness, sweetness, and complexity. Far from being a simple baking process, industrial chocolate roasting is a finely tuned science that must balance heat, time, air circulation, and even bean origin to unlock the flavor potential locked within the bean's cellular structure. The roasted profile of chocolate is not one size fits all. It varies greatly depending on the origin of the beans, the desired flavor profile of the final product, and the style of chocolate being produced, whether it's milk, dark, or even single origin specialty bars. As such, chocolate factories have roasting protocols tailored to each bean variety and product type. These protocols are logged as roast profiles, charts that map temperature over time, often broken into phases: drying, browning, and development. Each phase requires precise thermal input and airflow to extract the right flavors without burning or flattening the bean. Industrial chocolate factories use several types of roasters depending on scale and product goals. The most common are batch drum roasters and continuous roasters. Batch drum roasters, similar in design to coffee roasters but much larger, feature a rotating cylindrical drum made from stainless steel. Beans are loaded into the drum, which rotates over direct or indirect heat, with hot air circulated through the drum chamber. Temperature sensors embedded in the drum monitor the bean mass, ambient air, and exhaust temperatures simultaneously. Factory operators can adjust drum speed, airflow rate, and burner intensity through PLC-controlled interfaces to manage the roast curve. Roasting typically begins at a lower temperature, around 100 degrees Celsius, to drive off any remaining surface moisture. This is the drying phase and usually lasts for 5 to 10 minutes. The beans then enter the browning phase, where the Maillard reaction begins. This is the chemical process that causes amino acids and reducing sugars in the beans to recombine and form hundreds of flavor compounds: nutty, roasted, caramelized, and acidic notes that are essential for chocolate's complexity. This phase is carefully controlled, usually taking another 10 to 15 minutes, with bean temperatures rising to 120–140 degrees Celsius. The final stage of roasting is known as development, or the finishing phase. Here, the beans are brought to their final internal temperature, typically between 135 degrees Celsius and 150 degrees Celsius, depending on the desired flavor profile. This phase is brief, often just 2 to 5 minutes, but it's critically important. Too little development, and the flavor may be grassy or underwhelming. Too much, and the chocolate may taste burnt, acrid, or flat. Advanced factories use real-time infrared cameras and bean temperature probes to monitor this phase with incredible accuracy, sometimes recording temperatures at 1-second intervals. After roasting, the beans must be cooled quickly to halt the cooking process. This is usually achieved in a dedicated cooling drum or tray system, where ambient or chilled air is blown across the beans using high-speed fans. Cooling not only stops the roast, but it also firms up the bean shell and prevents steam buildup, which could cause condensation or spoilage during storage. At this point, the beans are dark brown, fragrant, and brittle, but they still contain their outer shells, a thin, papery husk that must be removed to access the valuable interior, the cacao nib. The next phase is known as winnowing. Winnowing is a mechanical process that cracks the beans open and separates the lightweight shells from the dense nibs using a combination of crushing and air classification. In a large-scale chocolate factory, beans are first passed through a pre-cracker or roll crusher, which breaks them into fragments of varying size. The cracked mixture is then fed into a winnowing chamber, often a series of vertical air columns or vibrating conveyor belts, where calibrated air jets or suction systems separate the heavier nibs from the lighter shells. The airflow is precisely tuned so that the nibs fall to the bottom collection bins while the husks are drawn upward into separate waste hoppers. The result is a batch of pure cacao nibs, dark, rich, and packed with flavor and cocoa solids. These nibs are now ready to be transformed into chocolate liquor, not an alcoholic beverage, but a thick, paste-like substance made from finely ground cacao nibs. This is where the chocolate truly begins to take shape. To produce liquor, The nibs are passed through industrial grinders known as pre-refiners or impact mills. These machines use either rotating steel blades or stone rollers to shear the nibs into smaller and smaller particles. As the nibs are ground, frictional heat causes the cocoa butter inside to melt. This transforms the mixture from a coarse, gritty powder into a flowing paste with a smooth, velvety texture. The grinding process typically reduces particle size to around 80 to 100 microns during this first stage. From here, the liquor is either held in heated tanks for further processing or sent directly to the next grinding phase, refining. Refining is the step where particle size is further reduced to achieve the smooth mouthfeel expected from high-quality chocolate. This is performed using 5-roll refiners or ball mills. 5-roll refiners consist of 5 horizontally stacked steel rollers, each rotating at a different speed. The chocolate liquor is fed into the gap between the rollers, which progressively shear the particles down to between 15 and 25 microns. At this size, individual cocoa and sugar particles are too small for the tongue to detect, giving chocolate its creamy texture. In factories producing sweetened chocolate, sugar is added during this refining phase. The sugar, already pre-milled to ensure consistent granule size, is blended with the chocolate liquor to form what's called a chocolate crumb. Depending on the recipe, milk powder, vanilla, lecithin, and other ingredients may also be added at this stage. These additions are carefully weighed and dosed using automated batching systems, which ensure that every batch conforms to a master formulation. After refining, the chocolate mass still feels dry and powdery. To turn it into a cohesive, pourable liquid with a smooth finish and stable flavor, it must undergo conching, a prolonged mixing and aeration process that can last anywhere from several hours to multiple days. Conching takes place in large heated vessels fitted with rotary arms or heavy granite rollers. The goal of conching is threefold: to develop flavor by oxidizing volatile acids, to smooth texture by distributing fat uniformly, and to improve viscosity by reducing moisture and undesirable compounds. The conching process is controlled in phases: dry conching, where the paste is crumbly and thick; plastic conching, where it softens and flows; and liquid conching, where the mass becomes fully fluid. Each conching profile is custom tailored to the specific chocolate type being produced. Milk chocolate, for instance, requires longer conching to balance milk solids and sugars, while high percentage dark chocolate may be conched shorter to retain more of its natural acidity and origin flavor. Throughout conching, temperature, shear force, and oxygen flow are all regulated. Some factories utilize closed-loop conches with nitrogen blanketing to reduce oxidation, while others incorporate vacuum systems to pull out undesirable volatile compounds. This stage is monitored using inline viscometers and gas sensors, ensuring consistent output from batch to batch. At this point in the process, the chocolate mixture has reached a smooth, glossy, and richly aromatic state. It flows as a thick liquid, its flavors matured and balanced from hours of careful mixing, grinding, and aeration. The next phase transforms that liquid mass into a finished, stable form suitable for packaging and distribution. This involves cooling and crystallizing the cocoa butter within the mixture in a very specific way, a stage that requires precision and control over time, temperature, and movement. The goal here is to encourage the formation of the right type of crystal structure in the cocoa butter. Cocoa butter can solidify into several different crystalline forms, but only one of them results in a final product that has a smooth surface, sharp snap, resistance to melting in the hand, and a stable shelf life. To achieve this, the entire mass must be carefully tempered. Tempering is carried out in machines built for continuous flow and temperature control. These tempering units begin by first heating the mixture slightly above the melting point of all crystal forms, typically around 45 degrees Celsius. This ensures that any existing crystal structures are completely melted away. The liquid is then cooled gradually, usually to somewhere between 26 degrees Celsius and 28 degrees Celsius, depending on the specific type being produced. During this cooling, movement is maintained through stirring blades and flow channels, allowing the desired type of stable crystal to begin forming. Once enough of these seeds have developed, the mixture is gently reheated to a precise finishing temperature, usually just under 32 degrees Celsius. This final temperature is critical. It allows the seeded crystals to remain while eliminating the unstable forms that would cause bloom or textural issues later on. The flow, agitation, and temperature must be maintained within a very tight range. Modern tempering equipment uses inline sensors and feedback control loops to monitor these values in real time, ensuring the product is correctly tempered before it moves into the next station. From here, the tempered liquid is conveyed to the molding lines. These are high-speed, fully automated systems designed to pour precise volumes into molds of various sizes and shapes. The molds themselves are preheated slightly to prevent premature setting and ensure even flow. As the mixture is deposited into each cavity, vibratory tables shake the molds to remove any trapped air bubbles and ensure a perfectly even distribution. Once filled and vibrated, the molds are sent through long cooling tunnels. These enclosed, refrigerated belt systems gradually reduce the temperature in controlled stages, allowing the internal structure to set without cracking or warping. The airflow, tunnel speed, and humidity are all precisely calibrated to avoid moisture condensation on the surface, which could lead to dull or sticky finishes. Once cooled and fully solidified, the bars or shapes are released from the molds using a combination of mechanical pushes and short bursts of air. The finished items are then transferred onto conveyors that lead to the inspection zone. Here, vision systems scan each piece for defects, looking for uneven surfaces, cracks, color inconsistency, or any signs of bloom. Imperfect units are automatically ejected from the line for recycling. In many operations, these rejected items are remelted and retempered to be used again in the next batch. From this point, the finished product moves toward wrapping and packaging. The type of packaging depends on the product format, whether individual bars, boxed assortments, filled shapes, or bulk items for further processing. For single bars, wrapping lines are designed to handle high volumes per minute. Each bar is conveyed through a wrapping machine that cuts, folds, and heat seals the wrapper with high-speed precision. These machines are synchronized with the flow of the production line to prevent jamming, tearing, or misalignment. Packaging materials include metallized films, waxed paper, biodegradable foils, or composite laminates. These materials are selected based on the storage requirements of the product, the region's environmental regulations, and the shelf life goals. Many manufacturers also include oxygen scavengers or modified atmosphere sealing to enhance freshness, especially for filled products. After wrapping, individual bars or pieces are grouped into larger cartons or boxes by pick-and-place robotics. These machines identify product orientation, pick them up using suction or mechanical fingers, and place them into retail boxes, display trays, or bulk cases. The outer cartons are sealed, labeled, and pass through final quality control scanners that confirm weight, barcode accuracy, and expiration coding. Palletizing comes next. Stacked and secured cartons are placed onto shipping pallets according to loading patterns that maximize space efficiency and minimize stress on the bottom layers. Pallets are shrink-wrapped using rotating arms or heat tunnels, and then labeled with shipping codes, batch numbers, and destination data. The entire production record for each batch is digitally logged in the factory's quality control database. This includes source information for the raw ingredients, roasting and grinding parameters, conching durations, tempering temperatures, molding timestamps, and final inspection results. Should any issue arise downstream in distribution or retail, the system allows full traceability back to the moment each unit was created. Finished pallets are moved to climate-controlled storage zones. These warehouse areas are kept at stable temperatures, generally between 16 degrees Celsius and 20 degrees Celsius, to prevent melting, blooming, or flavor degradation. Humidity is also controlled, often under 60%, to protect the product and packaging integrity. Some products are stored under specific lighting conditions to prevent discoloration, particularly white and milk varieties that are more sensitive to UV exposure. Finally, shipments are released according to production schedules aligned with distribution needs. Orders are grouped by destination region, retailer, or distributor and loaded into trucks, shipping containers, or cargo planes. Temperature data loggers may be placed inside shipments to confirm that climate conditions remain within acceptable limits throughout transport. Though the product has now left the facility, its connection to the factory process is never lost. Retail complaints, test results, or customer feedback can all be traced back to the specific day, shift, and equipment used. Manufacturers regularly run shelf life simulations, flavor degradation tests, and mechanical stress analyses on packaged goods to validate the effectiveness of the process long after the final product leaves the line. Every stage, from raw bean to packaged bar, is designed not just for efficiency, but for repeatability and control. Factories producing chocolate operate like laboratories with strict protocols, while still honoring the craft behind each ingredient's transformation. This combination of technical discipline and sensory artistry is what makes industrial chocolate manufacturing one of the most exacting and fascinating operations in the global food industry. Once the finished chocolate leaves the factory, perfectly tempered, molded, cooled, and sealed in its final packaging, the industrial process doesn't come to a halt. A crucial final phase still unfolds, one that ensures the product not only reaches shelves in perfect condition, but also maintains its quality and integrity through transportation, storage, retail display, and eventual consumption. This extended phase is managed through sophisticated logistics, environmental monitoring, supply chain coordination, and continuous quality assurance practices. While this may seem like the back end of production, it is deeply integrated into how chocolate is made and maintained on a global scale. Immediately after production, the packaged chocolate is transferred into climate-controlled storage areas within the factory's distribution wing. These areas are tightly regulated to prevent degradation. The ideal temperature for storing finished chocolate is generally between 16 degrees Celsius and 20 degrees Celsius, with humidity kept below 60%. Above this humidity threshold, there is risk of sugar bloom, a white, dusty coating that forms when moisture causes sugar to dissolve and then recrystallize on the surface. Below this range, especially in dry climates, static electricity and brittleness can become issues, particularly for filled or aerated varieties. Storage racks are arranged to allow airflow between pallets. Each pallet is tagged with a unique identifier and scanned into the warehouse management system. This allows the system to track not only where each batch is physically stored, but also how long it's been in inventory, where it needs to go next, and whether it's awaiting any last-minute quality hold releases. Before a batch can ship, a final set of post-production tests is sometimes performed on a sample group. These tests may include accelerated shelf life simulations, where chocolate is exposed to varying environmental conditions in climate chambers to determine how it performs over time. Texture analyzers may test for brittleness or softening, while gas chromatography may be used to check whether volatile flavor compounds remain stable. Once cleared, shipments are scheduled for distribution. Whether headed to a supermarket distribution center, a specialty retailer, or international export, The chocolate must be loaded into transport systems that preserve the exacting conditions it was stored under. This can involve refrigerated or climate-controlled trailers, especially for higher-end varieties or filled products that are more vulnerable to heat. During warmer seasons, some companies delay shipments until nightfall or equip their pallets with insulation wraps to preserve temperature during brief exposure windows. Transport vehicles are often equipped with onboard temperature loggers. These small, battery-powered devices record environmental conditions every few minutes and are reviewed upon delivery to confirm that there were no unacceptable spikes in heat or humidity. If the data shows a breach, the receiving party may reject the shipment, even if the exterior packaging appears untouched. This level of accountability ensures that the integrity of the product is never assumed, but always confirmed. At the retailer level, chocolate continues to face environmental risks. Supermarkets and convenience stores may place chocolate in non-refrigerated aisles where exposure to lighting, fluctuating temperatures, and air conditioning vents can impact quality. To mitigate this, factory teams sometimes conduct in-store audits, either directly or through contracted merchandising specialists. These audits include checks on product placement, shelf temperature, rotation practices, and visible quality. Manufacturers also perform pull tests, where random samples are purchased directly from stores and sent back to internal labs for analysis. This helps determine if the product maintains its texture, snap, and flavor after weeks or months in the distribution system. These real-world results are fed back into the production process, helping engineers refine shelf life goals, tweak packaging barrier specifications, or adjust emulsifier ratios for better thermal resilience. Despite this rigorous system, the industrial process isn't rigid. Many manufacturers now build flexibility into their operations to support seasonal releases, new flavor experiments, and evolving consumer preferences. This includes small batch production lines within large factories that can produce limited runs of new recipes without interrupting mass-scale output. Even with these small lines, all the same steps: roasting, refining, conching, tempering, molding, wrapping are followed precisely, but in more agile formats. The long arc of chocolate production, from tropical farm to factory and beyond, is a story of transformation, precision, and protection. Each stage is critical, from developing flavor precursors during fermentation, to unlocking complexity through roasting, to achieving that final, glossy finish through proper tempering and cooling. It's not just about creating a product, it's about preserving it, tracking it, testing it, and delivering it across continents in exactly the state it was intended. The process for M&Ms begins with the preparation of the chocolate centers. For classic milk chocolate M&Ms, this involves creating a standardized chocolate blend using a combination of cocoa liquor, cocoa butter, milk solids, sugar, and lecithin. These ingredients are carefully measured and introduced into large industrial mixing vats. The ratio of milk solids to cocoa and sugar is adjusted based on the exact product line, whether it's milk chocolate, peanut, crispy, or almond. Once blended, the mixture moves to a refining stage, typically using a 5-roll refiner. This machine grinds the chocolate particles to an optimal size, usually under 25 microns, to ensure a smooth texture without any detectable grittiness. Following refining, the chocolate mass is transferred into conche machines, where it is continuously mixed and aerated under controlled heat. This critical step, often lasting up to several hours, develops the final flavor by driving off acidic compounds and ensuring that all ingredients are evenly emulsified. After conching, the chocolate is cooled and pumped into a tempering machine. Here, the chocolate is brought through a series of controlled heating and cooling stages to encourage the formation of stable cocoa butter crystals. This tempering process is essential for the final snap and sheen of the chocolate. Tempered chocolate is held in insulated storage tanks, stirred continuously to maintain consistency and prevent premature crystallization. To form the centers of M&Ms, the tempered chocolate is deposited into spinning molding drums, where small, consistent droplets are rapidly cooled to form uniformly sized spheres. In the case of peanut or almond M&Ms, the center process is different. Whole nuts are cleaned, dry roasted to exact specifications, and then tumbled in pans where successive layers of tempered chocolate are applied. Each pass adds a thin layer, and between coatings, the centers are cooled and stabilized to maintain roundness and uniform chocolate coverage. Once the chocolate cores, whether solid chocolate or chocolate-covered nuts, are ready, they are transferred to the panning room for sugar shell application. This is one of the most technically demanding parts of the process. The cores are loaded into large rotating pans, or dragée pans, that slowly tumble the centers while a thin sugar solution is sprayed onto them. As the pans rotate, the solution spreads evenly, and heated, dehumidified air is blown into the pans to evaporate moisture and crystallize the sugar coating. This process is repeated dozens of times. Each cycle deposits a very thin layer of sugar, which is dried and hardened before the next layer is applied. Through this repeated layering, the sugar shell grows gradually until the desired thickness is achieved. The conditions in the panning room are carefully controlled, with temperature, humidity, and airflow all precisely calibrated to prevent cracking, clumping, or uneven coatings. As the shelling nears completion, food-grade dyes are added to create the iconic M&M's color palette. Color application is done by loading batches into separate pans for each color. Liquid or powdered food coloring is sprayed or dusted over the still rotating candies, then sealed with a final transparent sugar polish. This step not only gives the candies their vibrant hues, but also produces the glossy finish M&Ms are known for. Modern facilities use optical scanners and machine learning algorithms to ensure each piece has uniform color coverage and no significant defects. Once the candy shells are colored and polished, the next step is the addition of the iconic M stamp. This is performed by a specialized printer equipped with multiple high-speed stamping heads. The M&Ms are spread out on a flat, vibrating conveyor belt that orients the candies so they're properly positioned for printing. Each printer head rapidly applies a food-safe white vegetable ink in the form of the lowercase m. The process is fast enough to stamp tens of thousands of candies per minute while maintaining alignment and clarity. After stamping, the candies are funneled into stainless steel hoppers where they cool briefly and are gently tumbled to remove any residual static electricity or misalignment. The candies then flow into the packaging line, which is equally sophisticated. M&Ms are portioned using multi-head combination weighers that ensure each packet receives an accurate fill weight. These weighers use vibrating chutes and load cells to dispense candies into forming machines that create the signature M&M's pouches or tubes from printed film. The packaging film is pulled, cut, and sealed around the candies in a vertical form-fill seal machine. Each pack is marked with a lot number, expiration date, and manufacturing code. Metal detectors and X-ray systems scan every packet for potential contaminants or packaging defects, and inline check weighers verify that the fill weight meets specifications. Any defective packs are ejected from the line automatically. Packaged M&Ms are then collected into cartons, which are barcoded and shrink-wrapped for shipping. These cartons are palletized by robotic arms and moved to climate-controlled warehouses. The temperature and humidity of these storage facilities are tightly controlled to prevent chocolate bloom or sugar shell degradation. The final step is distribution, with pallets sent out through a carefully coordinated logistics network to grocery stores, vending machines, and distributors around the world. Throughout the entire M&M's manufacturing process, quality control is constant. samples are pulled at every major stage: chocolate refining, shell coating, coloring, stamping, and packaging. Technicians perform tests on texture, shell thickness, moisture levels, and color uniformity. Tasting panels sample daily to assess flavor, and sensory booths are used to eliminate bias during evaluations. Environmental considerations are also built into the process. Dust collection systems are used in sugar handling areas to minimize air particulates, and water used in cleaning is recycled where possible using filtration and sterilization. Temperature recovery systems reuse heat generated by panning dryers and conching machines, feeding it into the plant's HVAC system or hot water circuits. In modern M&M's facilities, much of this process is overseen by a central digital control room. Here, operators monitor flow rates, temperature curves, humidity levels, and output speeds in real time across multiple screens. Any deviation from target specifications triggers alerts, enabling rapid correction before quality is compromised. Machine learning algorithms analyze production data to forecast maintenance needs, optimize energy consumption, and predict the impact of recipe tweaks. So, while a single M&M candy may seem simple, just a tiny bite of chocolate with a hard shell, it is in fact the result of a multi-stage, intricately controlled system designed for scale, precision, and repeatability. Each piece is the culmination of decades of engineering, from chocolate particle refinement and shell layering to robotic stamping and data-driven packaging. The result is a product that delivers the same color, crunch, and creamy center millions of times a day all over the world. Wafer production begins with the precise mixing of a liquid batter made from wheat flour, sugar, vegetable oils, leavening agents, salt, and water. This mixture is pumped into a pressurized holding tank, kept under constant agitation to maintain uniformity. From there, it flows into a series of wafer baking plates arranged on a rotary belt oven. Each set of plates clamps down, spreading the batter evenly across the mold surface as it rotates through a high-temperature tunnel oven. The baking process takes less than 2 minutes, during which the wafer sheets are cooked evenly on both sides to a crisp, golden consistency. Optical sensors mounted along the oven track monitor browning levels and moisture content in real time, adjusting heat distribution if necessary. The fully baked wafer sheets exit the oven onto cooling conveyors equipped with forced air fans. Rapid dry cooling is critical to avoid humidity absorption, which could lead to soggy or uneven wafers. Once cooled, the wafer sheets are transferred to a stacking unit where they are automatically aligned and fed into the layering system. This system applies a uniform layer of chocolate-based filling using a grooved roller that spreads the cream with millimeter precision. This filling consists of sugar, cocoa powder, non-hydrogenated fats, and finely ground reprocessed wafers, which are reincorporated into the cream to create a consistent texture and minimize waste. Another baked wafer sheet is pressed on top, forming the next layer. Most Kit Kat bars use 3 wafer layers and 2 cream layers in alternating sequence. The stacked wafer blocks pass under a compression roller to ensure uniform density and adhesion between layers. Immediately afterward, the layered wafer slabs are conveyed to the cutting station. High-speed rotary blades or ultrasonic knives slice the slab into individual fingers. Each cut must be surgically clean to preserve the structural integrity of the wafer and prevent crumbling or edge collapse. Blades are cleaned automatically between cycles to prevent buildup. Next, the naked fingers proceed to the enrobing line. These bare wafer pieces are gently placed onto stainless steel mesh conveyors and passed through a flow of tempered chocolate. The enrober coats each finger completely, sides, bottom, and top, with a thin, even layer of chocolate. To prevent excess chocolate from accumulating at the base, Air knives blow from underneath the mesh to clear pooling, followed by a vibrating section that helps settle the coating and eliminate surface bubbles. Tempering of the enrobing chocolate is critical here. The chocolate must be heated, cooled, and reheated in a precise sequence to promote stable cocoa butter crystallization. This gives the final product its distinctive glossy finish and crisp snap. Chocolate that isn't properly tempered can appear dull, bloom with fat crystals, or become too soft at room temperature. Once coated, the fingers are passed through a cooling tunnel that gradually reduces the temperature from about 30 degrees Celsius down to 10 degrees Celsius. This controlled descent ensures the chocolate solidifies uniformly without contracting too quickly or developing cracks. Cooling typically takes around 5 to 7 minutes and is performed in multiple zones, each with its own humidity and temperature controls. Sensors inside the tunnel detect surface gloss and chocolate hardness using reflectometers and pressure probes. If any deviation is found, the product is automatically diverted for reprocessing. At this point, the bars are ready for the branding stage. For standard 4-finger Kit Kats, an embossing stamp may be used to imprint the brand name into the chocolate coating while it's still slightly soft, just before final hardening. The embossed chocolate then continues along the line to the packaging area. Bars are counted, aligned, and guided into flow wrappers. A single horizontal form-fill seal machine wraps each bar in a foil laminate film printed with branding, nutritional information, barcodes, and lot numbers. The film is heat-sealed around the chocolate in less than half a second, forming a tight, protective package. Each wrapped bar is then weighed using an inline check weigher to ensure proper chocolate fill and detect any anomalies. If the bar is too light or heavy, or if the seal is not correctly formed, it is rejected and sent to a secondary inspection lane. Successful bars are collected into batches for secondary packaging. This may include multi-packs, gift boxes, or variety bundles, depending on the product variant. Robotic arms arrange bars into trays or cartons, which are then sealed, labeled, and date-stamped by automatic systems. These boxes are stacked on pallets using robotic palletizers programmed with pattern optimization software to maximize space efficiency and ensure load stability. The completed pallets are shrink-wrapped and tagged with RFID identifiers that record batch data, origin, and destination logistics. Finished pallets are transferred to a temperature-controlled warehouse maintained between 16 degrees Celsius and 20 degrees Celsius with 45 to 55% humidity, ideal storage conditions to prevent chocolate bloom and preserve crunch in the wafers. All stages of production are monitored via a centralized manufacturing execution system, which links real-time sensor data, production schedules, and quality control checkpoints. Operators monitor dashboards that display belt speeds, oven temperature graphs, chocolate viscosity readings, packaging line uptime, and rejection rates. Every wafer, batch of chocolate, and final bar is fully traceable from ingredient origin to final pack, enabling precise recall or investigation in the rare case of a defect. Clean-in-place systems are integrated into most parts of the equipment, allowing the factory to perform daily automated cleaning cycles without disassembling major machinery. Water and detergent are flushed through piping, tanks, and depositor heads, followed by steam sterilization and final air purging. Swab tests and microbial sampling are done routinely, especially after allergen changeovers, such as moving between milk and dark chocolate lines or introducing limited edition flavors. The process of making Kit Kat bars, though outwardly simple in concept, wafers layered with cream and enrobed in chocolate, is actually one of finely balanced engineering. The crunch of the wafer, the creamy consistency of the filling, the uniformity of the chocolate coating, and even the tension of the foil wrap all contribute to a product that is as much about texture and satisfaction as it is about taste. Every part of the factory, from mixing vats to wrapping stations, operates in harmony to produce millions of identical bars that deliver the same experience each time. But Snickers' manufacturing process is even more impressive. Whole roasted peanuts arrive at the factory in bulk shipments and are immediately transferred into stainless steel holding silos equipped with air filtration and pneumatic transport systems. Before they're used, the peanuts are screened, sampled, and scanned for foreign materials using advanced sorting lines that include vibration screens, metal detectors, and high-speed optical sorters. Any discolored, shriveled, or malformed nuts are rejected. The selected peanuts are conveyed to large rotary roasters, where they are slowly tumbled in hot air at around 160 to 180 degrees Celsius. This roasting stage is critical, not only for flavor, but for ensuring that the final texture of the peanuts remains crunchy after they're embedded in caramel. Once the roasting cycle is complete, the peanuts are cooled rapidly using forced air systems to halt the cooking process and stabilize their structure. While the peanuts are being prepped, the caramel layer is produced in parallel. Granulated sugar, glucose syrup, sweetened condensed milk, and a blend of fats are mixed in steam-jacketed kettles with constant agitation. The mixture is heated to between 115 and 125 degrees Celsius, which caramelizes the sugars and thickens the mass. The cooking time and temperature are tightly controlled to achieve the exact stretchiness and chew required. Too soft, and it won't hold its shape in the bar. Too hard, and it becomes brittle. As the caramel nears its final temperature, milk proteins begin to break down, giving the mixture its signature golden color and deep, buttery flavor. Once ready, the caramel is pumped through heated pipes to a depositor, where it will be applied in a uniform sheet. The nougat layer, found beneath the caramel and peanuts, is created on a separate line. This begins with whipping a blend of sugar, glucose syrup, dried egg whites or hydrolyzed proteins, and milk solids in large planetary mixers. Nitrogen gas is injected during this mixing process to aerate the nougat, creating its signature light and chewy consistency. This mixture is then folded with a chocolate paste made from cocoa powder and oils to give Snickers nougat its slightly chocolatey tone. Once fully mixed, the nougat is extruded through wide slits onto a continuously moving belt to form a long, flat sheet that cools as it travels down the line. The caramel is poured directly onto the cooled nougat slab as it moves along the conveyor, forming the second distinct layer. Immediately after, the roasted peanuts are evenly scattered onto the still warm caramel using a vibratory spreader, ensuring every inch of the bar's width receives a consistent peanut distribution. Timing here is crucial. The caramel must be warm enough for the peanuts to adhere properly, but not so hot that they sink in or shift. This three-layer sheet, nougat, caramel, and peanuts, is allowed to set slightly before it moves into the slabbing station. Here, precision blades cut the wide slab into long, narrow ribbons. These ribbons are then rotated 90 degrees and fed into guillotine-style cutters that chop them into bar-length pieces. Each bar is now in its final shape, but still lacks the chocolate coating that completes the Snickers experience. The uncoated bars are lined up and transferred to the enrobing system. As they move along the stainless steel mesh conveyor, they pass beneath a curtain of tempered milk chocolate. This coating is supplied from a dedicated tempering machine that brings the chocolate through carefully managed heat cycles to promote the formation of stable cocoa butter crystals. The chocolate is heated to around 45 degrees Celsius to fully melt it, cooled to about 27 degrees Celsius to initiate crystal formation, and then gently reheated to 30 to 32 degrees Celsius to achieve the right viscosity and gloss. The bars pass under this curtain of chocolate, completely coating their tops and sides. Simultaneously, the conveyor dips the bars through a shallow reservoir of chocolate to coat their undersides. Immediately after enrobing, the bars are passed through a vibrating section and gentle air jets. The vibration removes any excess chocolate and smooths the surface, while the air jets help eliminate bubbles or irregularities. A final grooved roller may be used to apply a signature wave texture to the top of each bar before they enter the cooling tunnel. The cooling tunnel consists of a long, temperature-zoned chamber that gradually reduces the bar's internal and surface temperatures from the low 30s down to around 10 degrees Celsius. Cooling is done in stages to prevent thermal shock, which could cause chocolate to bloom or the caramel to separate. The humidity is also carefully controlled to prevent condensation or sugar crystallization. As the bars move through this tunnel over several minutes, the chocolate hardens into a stable, glossy shell that encases the caramel, peanuts, and nougat within. After cooling, the bars are discharged onto a secondary conveyor where they are spaced, aligned, and funneled into the wrapping line. Here, a horizontal form-fill seal machine envelops each bar in a printed plastic film that's been preloaded with branding, nutritional information, barcodes, and lot tracking data. The wrapping film is heat-sealed around the bar and trimmed using rotary knives. Wrapping is synchronized precisely with the movement of each bar to prevent any misalignment or creases. After wrapping, the bars are scanned by metal detectors to ensure no metallic contamination has occurred during production. They're then passed through check weighers to confirm each bar falls within the designated weight tolerance. Any bar that falls outside these parameters is rejected automatically and sent to a collection point for analysis or recycling. Approved bars are sorted into cartons using robotic arms that can grip and group them based on SKU. These cartons are then sealed, coded, and stacked onto pallets using automated palletizers. Each pallet receives a printed label with batch information, destination codes, and compliance data. Before leaving the facility, all pallets are shrink-wrapped and staged in a temperature-controlled warehouse area where storage conditions are maintained between 16 and 20 degrees Celsius with less than 50% relative humidity. A centralized control room oversees all operations using real-time data collected from each machine to ensure consistency and efficiency. Key metrics such as temperature curves, mixing durations, chocolate viscosity, output rates, and rejection levels are displayed on screens for operators and engineers to monitor. Any deviation outside acceptable tolerances triggers alerts and corrective actions, which are logged into the production management system for traceability. Production changeovers, such as switching between regular Snickers and Snickers almond or Snickers peanut butter, involve flushing the lines, sanitizing all contact surfaces, and performing allergen checks. Cleaning is often done with clean-in-place systems, which circulate heated detergents and rinse water through enclosed tanks, pipes, and pumps. Swab tests and visual inspections verify cleanliness before the next product is introduced. Throughout the process, quality assurance teams take samples at each stage, from nougat aeration to enrobing, for analysis. These samples are tested for moisture content, density, layer thickness, chocolate coating weight, and overall structure. Finished bars are also subjected to sensory testing by trained panels, who evaluate appearance, flavor balance, aroma, and mouthfeel. Sustainability measures are integrated into production as well. Heat generated from the roasters and tempering units is recaptured and used to pre-warm wash water or facility air. Water used for cleaning is filtered and reused in non-product contact systems. Packaging film is sourced from suppliers that meet recyclability and food safety standards, and efforts are ongoing to reduce the environmental footprint of the wrapping process. Every Snickers bar, while simple in form, is a result of hundreds of interlocked operations, each designed for speed, hygiene, consistency, and indulgent quality. The chewy nougat, stretchy caramel, roasted peanuts, and milk chocolate coating are all optimized for flavor release, structural contrast, and a repeatable experience in every bite. From roasting to wrapping, this process is replicated across multiple global production facilities, each maintaining the same high standards to deliver one of the world's best-selling. The manufacturing journey of Doritos begins long before the chips ever hit the fryer or the seasoning drums. It starts in the cornfields. Doritos use a specific variety of whole kernel yellow corn selected for its starch content, moisture levels, and particle uniformity after grinding. The corn is harvested at peak maturity and tested for aflatoxins, foreign material, and protein content before it's even accepted at the plant. Only corn that passes this first round of quality standards is brought in for processing. At the factory, truckloads of bulk corn arrive daily and are funneled into underground receiving pits that use gravity to guide the kernels onto conveyor belts. These conveyors feed the kernels into the first stage of preparation, the cleaning and sorting system. In this system, the corn passes through an array of vibrating sieves, rotating drum sifters, and powerful pneumatic air classifiers. Large debris like cobs, sticks, or stones are removed first. Then, finer contaminants like dust and small broken kernels are extracted using aspirators that draw away lightweight particles. Magnetized rollers also scan the corn flow to remove any traces of ferrous metal, ensuring total cleanliness before cooking. Once cleaned, the corn moves into the nixtamalization phase, a crucial and traditional process that transforms the flavor, texture, and nutritional properties of the corn. Nixtamalization involves cooking the whole kernels in a large stainless steel vat of hot water mixed with food-grade calcium hydroxide, also known as slaked lime. The corn is cooked at around 85 to 90 degrees Celsius for approximately 20 to 40 minutes, depending on the batch size and corn variety. This lime water solution serves several purposes. It breaks down the outer pericarp of the kernel, making it easier to grind and digest. It also increases the bioavailability of niacin, softens the internal structure of the corn, and imparts the distinctive flavor profile that Doritos are known for. After cooking, the corn is not immediately processed but left to soak, usually for 8 to 12 hours in the same solution. This extended soaking allows the lime to fully penetrate the kernel and continues the softening and flavor-enhancing process. After the soaking phase, the corn is drained and rinsed thoroughly in large industrial washers that spray it with jets of clean water while gently tumbling the kernels. The goal is to remove the loosened pericarp, excess lime, and any residual cooking liquid. What remains is called nixtamal, a soft, pliable corn mass that still holds the shape of whole kernels, but has a meaty, hydrated texture. The nixtamal is now ready to be ground into masa, the dough-like base of every Dorito chip. The grinding is performed using industrial stone mills, rotating horizontal stones made of volcanic rock or synthetic composites, precisely aligned to maintain a consistent grind size. The nixtamal is fed between the stones, and the pressure shears the softened corn into a dense, cohesive paste. This paste is the masa, and its texture is critical. It needs to be soft enough to press, but dry enough to hold shape without sticking. Operators continuously monitor the temperature of the mesa during grinding. Too much friction can overheat the dough, which affects the final chip texture. Ideal mesa temperature coming off the stones is around 45 to 55 degrees Celsius. Viscosity is checked using inline sensors that measure flow resistance, and if adjustments are needed, small amounts of water or return dry mesa are mixed back in using an automated feedback loop. Now it's time to form the masa into flat sheets. The ground mesa is transported via auger screws into a sheeting machine, which extrudes the dough between two polished stainless steel rollers. These rollers are adjustable to control sheet thickness down to the millimeter, usually targeting between 1.2 and 1.8 mm, depending on the final chip specification. The mesa sheets are laid directly onto a continuously moving conveyor belt that carries them to the cutting station. The cutting system is a rotary die cutter, a high-speed drum outfitted with rows of equidistant triangular blades, each perfectly matched to the iconic Doritos shape. As the mesa sheet moves beneath the drum, the rotating blades stamp out thousands of identical triangle chips per minute. Each cut is sharp and precise, with just enough spacing to leave minimal waste dough between cuts. The trimmings, the thin slivers of masa between triangles, are not discarded. They are automatically lifted via vacuum collection and returned to the start of the sheeting process. These scraps are reincorporated into the fresh dough, ensuring efficient use of material and maintaining consistency. The cut triangle chips now move on a flat conveyor to a brief baking phase, which we'll explore in detail in the next section. This preliminary baking is vital to reduce moisture and stabilize the chip before it enters the high heat frying zone. But before any oil is introduced or seasonings are applied, this early stage, cleaning, nixtamalization, grinding, sheeting, and cutting, is where the foundation of Doritos' crunch, shape, and flavor truly begins. Once the precisely cut mesa triangles are formed and conveyed forward, they reach one of the most critical transitions in the Doritos factory, the pre-baking zone. Though often overlooked, this short but essential phase serves as a structural stabilizer that prepares each chip for frying without deforming, bubbling uncontrollably, or becoming overly saturated with oil. This stage controls the internal moisture content and builds the texture foundation that will result in the signature crunch. The masa triangles, still soft and slightly tacky from the sheeting process, move onto a continuous metal mesh conveyor belt that leads directly into an industrial tunnel oven. This pre-bake oven is not designed to fully cook or brown the chip. Instead, its primary goal is to reduce the moisture level from roughly 50% down to about 25 to 30%. This ensures the surface of the chip becomes firm enough to hold its shape when exposed to hot oil, but not so dry that it resists expansion. The oven itself is typically divided into multiple thermal zones. The first zone begins around 160 degrees Celsius, gradually increasing to about 260 degrees Celsius by the final section. Heated air is circulated by high-velocity blowers, creating a turbulent flow across the top and bottom of the chips to ensure uniform dehydration. The baking conveyor is made of stainless steel mesh that allows hot air to penetrate from below, guaranteeing that no side of the chip is undercooked. Sensors monitor humidity at various checkpoints, and real-time data is fed into the oven's PLC system to dynamically adjust airspeed and temperature depending on fluctuations in mesa density, ambient humidity, or line speed. As the chips exit the oven, they emerge firmer, drier, and more resilient, yet still pale in color and lacking the blistered surface texture that defines a finished Dorito. That transformation happens in the next stage, the continuous fryer system. Here, the par-baked chips fall gently off the oven belt and descend onto the infeed section of a massive open-surface fryer. The fryer itself is a high-capacity stainless steel vessel filled with continuously filtered cooking oil. Most Doritos production lines use either corn oil, sunflower oil, or a proprietary blend of vegetable oils chosen for their high smoke points and neutral flavor profiles. The oil is maintained at a stable frying temperature of approximately 180 degrees Celsius, with variations of only plus 2 GC allowed during operation. Chips are submerged in the oil for about 35 to 55 seconds, depending on their exact moisture level and thickness. The chips ride through the fryer on a submersion conveyor, essentially a mesh belt with downward pressure bars that keep the chips fully immersed while preventing stacking or overlap. This is crucial because the frying process is not just about dehydration, it's about vaporization. As the residual water inside each chip turns to steam, it forces itself outward, puffing the chip slightly and creating those micro blisters and bubbly textures on the surface. This internal steam pressure is carefully managed. Too little and the chip stays flat and hard. Too much, and it balloons into a hollow pocket. Above the fryer, exhaust hoods pull away steam and vaporized oil particles, filtering them through a heat recovery system that can reuse waste heat to pre-warm incoming oil. This system conserves energy and helps maintain a cleaner frying environment. The oil itself is constantly recirculated through centrifugal filters and fine mesh screens to remove crumbs, starch residues, or burnt particles. Fresh oil is added in controlled volumes throughout the day to maintain chemical balance and replenish lost volume. Once fried to the optimal light, golden color, the chips are lifted from the oil by an outfeed conveyor and immediately pass through a vertical de-oiling section. Here, powerful centrifugal blowers aimed at precise angles blast away excess surface oil. This keeps the chips crispy, prevents pooling in the packaging stage, and ensures that the seasoning will stick without creating grease buildup. The chips then pass through an ambient cooling tunnel to bring them quickly down to room temperature. Cooling is not merely for worker safety, it stabilizes the fat within the chip and prevents condensation when entering the seasoning drums. Now comes one of the most defining stages of the entire process: seasoning application. Each Dorito must carry the bold, vibrant flavor profile it's known for, whether that's nacho cheese, Cool Ranch, spicy sweet chili, or any of the dozens of global variants. The seasoning powder itself is a proprietary blend of flavorings, including real cheese powders, spices, salt, sugar, yeast extract, and encapsulated flavor oils that deliver controlled release bursts of taste. The chips are conveyed into a rotating seasoning drum, an inclined, slowly turning cylinder lined with food-grade stainless steel. As the chips tumble over one another, a dry powder dosing system mounted above the drum applies the seasoning using precision augers and dispersing nozzles. These nozzles can spray a uniform mist of oil if needed before the seasoning hits, which enhances adhesion for certain formulations. The rotation speed of the drum, the flow rate of the powder, and the incline of the system are all adjustable and carefully tuned. Too slow, and the powder won't distribute evenly. Too fast, and the chips may break, or the powder may collect unevenly on some sides. Optical sensors track the color and surface reflectivity of the chips as they exit the drum. If the reflectivity is too high, that could indicate under-seasoning. If it drops below a preset threshold, over-seasoning may be occurring. This live data is fed back into the controller, which tweaks the feed auger speed or pauses the oil spray accordingly. The seasoning drum is one of the most customized parts of the Doritos line. Different flavors use different particle sizes, densities, and oil volumes, which means the drum design and spray system must adapt depending on the product. Some drums include vibrating baffles or spiral lifts that increase tumbling action for extra thick chips or extra coarse seasoning. Once seasoned, the chips are directed into the weighing and bagging system, but before that, they undergo an automated inspection phase. High-speed vision cameras scan every chip for size, shape, and color. Broken chips, overly curled pieces, or visibly under-seasoned chips are removed via air-jet rejectors. These rejected chips are collected and sent either for regrinding or biomass energy use. Only chips that pass inspection enter the multi-head weighers, machines equipped with a dozen or more radial weighing hoppers. These hoppers constantly drop chips into a central collection bucket when the combined weight equals the target for each bag, typically between 28 g and 198 g, depending on package size. Once a precise combination is reached, the chips are dropped into a vertical form-fill-seal bagging machine. Here, continuous rolls of metallized polypropylene film are formed into tubes, sealed along the sides, and crimped at the bottom. The weighed chips are dropped into the formed bag tube just before the top is sealed and cut. Each bag is nitrogen flushed to displace oxygen, extending the product's shelf life and preserving crunch. Then, The bags are labeled, batch coded, and pass through a final metal detector before being boxed for palletization. After the freshly seasoned Doritos chips are individually weighed, bagged, sealed, and inspected, the production line moves into the critical post-packaging and logistics phase, where efficiency and traceability become as important as taste and texture. Though the chips are now fully formed and flavor complete, the operation is far from over. In fact, from a manufacturing systems perspective, the next stages, palletization, storage, shipping, and quality verification, are just as sophisticated and optimized as any in the earlier production line. The newly filled Doritos bags exit the form fill seal machines onto a series of conveyor belts designed to collect, orient, and organize them by SKU, bag size, and flavor variant. These conveyor lines merge into case packing stations, which use robotic arms equipped with vacuum suction grippers or gentle mechanical paddles to lift and place the chip bags into cardboard cartons. These boxes are pre-folded, glued, and printed with relevant product information, including product code, flavor, best before date, factory location, and a scannable QR or barcode that links to all production details. Each carton is inspected for weight and shape before it moves to the next phase. Even slight deviations in shape, caused by mispacked bags or an uneven number of chips, can disrupt downstream palletizing operations, so edge integrity and sealing quality are monitored automatically using high-resolution 3D scanning systems. Any carton that fails to meet dimensional tolerance is rejected from the main flow and rerouted for manual inspection or reboxing. Once cleared, the filled cartons are transferred to automated palletizing stations. In most modern Doritos factories, this process is entirely robotic. A multi-axis robotic arm lifts groups of cartons and stacks them onto wooden or composite pallets according to a predefined stacking pattern optimized for shipping efficiency and stability. These patterns are determined by a logistics algorithm that accounts for box dimensions, weight distribution, and the pallet's ultimate destination, whether that's a domestic warehouse or a long-haul overseas container. After each pallet is completed, a robotic stretch wrapper encircles it with several layers of clear plastic film to stabilize the load. A printed pallet ID label is affixed, containing detailed information about its contents, including product types, quantities, batch numbers, and destination. These labels are scanned into the warehouse management system, linking each pallet to the larger production database in real time. From here, pallets are routed into the warehouse zone. Doritos production facilities feature climate-controlled warehouses designed to maintain product quality throughout the storage period before distribution. These zones are not refrigerated, as Doritos are shelf-stable, but they are meticulously managed to avoid conditions that could lead to staleness or packaging deformation. Temperatures are generally held between 18-22 degrees Celsius, and humidity is controlled below 50% to prevent foil bags from absorbing moisture or warping. Inventory in the warehouse is managed by automated storage and retrieval systems. Tall racking structures are navigated by robotic cranes that pick and place pallets based on real-time demand, stock rotation policies, and shipping schedules. Each pallet's position in the warehouse is logged down to the specific shelf and column level, making retrieval highly efficient. The warehouse management system is integrated with the factory's enterprise resource planning software, ensuring that production and distribution are fully synchronized. While in storage, every pallet of Doritos is subject to randomized quality control sampling. A team of trained technicians removes sample bags from various pallets across shifts and production lines and sends them to a separate sensory evaluation lab within the facility. Here, samples undergo a series of tests: mechanical compression for bag integrity, gas analysis for nitrogen content, and oxygen intrusion, seasoning density checks, and most importantly, taste and crunch testing. Crunch is measured using a texture analyzer, a machine that applies controlled force to the chip and records resistance, fracture point, and acoustic feedback. The results are compared to golden standard reference chips to determine if the texture profile remains within acceptable limits. Seasoning adhesion and intensity are tested via flavor profile mapping, and every element from saltiness to umami to residual aftertaste is scored and compared against target values. If a trend of inconsistency is detected, an investigation is initiated, often leading to a review of upstream production parameters like fry temperature variability, seasoning drum throughput, or even ingredient batch variations. This closed-loop system helps prevent long-term quality drift and enables real-time course correction. Beyond the factory, the logistics infrastructure that gets Doritos from warehouse to retail shelves is another marvel of scale and precision. The factory works in tandem with PepsiCo's broader distribution network, which includes regional distribution centers, cross-dock terminals, and last-mile delivery nodes. Based on retail demand forecasts drawn from sales data, seasonal trends, and real-time POS metrics, shipment volumes are adjusted dynamically. This avoids overproduction and waste while ensuring retailers remain stocked. Each shipment of Doritos is accompanied by a digital bill of materials, which includes all traceability data from ingredient sourcing to packaging and palletization. This document allows not only for internal tracking, but also rapid action in the event of any product recall or customer complaint. If an issue is raised about a particular bag, say under-seasoning in a certain region, operators can trace the issue back to a specific lot, machine, shift, and even the original corn batch used in production. Globally, the manufacturing process for Doritos is also adapted based on regional consumer preferences and regulatory standards. While the foundational steps remain consistent, nixtamalization, sheeting, cutting, frying, and seasoning, the recipes and specifications can vary significantly. For example, in the US, cheese-based seasonings often use cheddar powder and lactic acid for tang, while in the UK or India, formulations may include less salt or alternative flavor enhancers to meet local guidelines or taste expectations. In markets like Japan or South Korea, where flavor sophistication and novelty are highly valued, factories produce limited edition Doritos featuring ingredients like wasabi, squid ink, or yuzu citrus. These variations often require changes in seasoning particle size, oil stability, or packaging material, and as such, the production lines must remain flexible. To facilitate this, Doritos factories use modular flavor dosing systems and quick changeover machines that allow seamless transitions between variants with minimal downtime. In addition to this flexibility, Doritos production lines are increasingly being outfitted with smart factory technologies. These include IoT sensors, predictive maintenance platforms, and AI-driven scheduling software. For instance, a vibration sensor might detect a subtle change in the seasoning drum's motor function that suggests a bearing is beginning to fail. Rather than waiting for a breakdown, the system automatically schedules maintenance during a planned production lull, avoiding unplanned downtime. Energy efficiency is also a growing focus. Waste heat from the fryers is often recovered through heat exchangers and used to preheat water for the nixtamalization tanks or warm the air in the seasoning room. Air filtration systems recycle hot air from the fryer exhaust into the building's HVAC to reduce natural gas usage. These sustainability practices help reduce both costs and environmental impact. Waste reduction is another area of innovation. Trimmings from mesa sheeting, broken chips, and seasoning dust are no longer treated as loss. Instead, they're collected, analyzed, and often reused in animal feed production, compost systems, or converted into biofuel at third-party processing facilities. Factory waste targets are set annually, and each production shift is scored on both yield efficiency and environmental impact. Ultimately, the journey of a Dorito from corn kernel to crunchy triangle is one of constant refinement. At every stage, whether it's dough hydration, fryer calibration, seasoning density, or robotic case packing, the process is governed by a matrix of mechanical precision and human sensory experience. The chips may seem simple to the average consumer, but behind every bag lies a production system that blends food science, industrial engineering, supply chain logistics, and consumer psychology into one unmistakable result: bold flavor, addictive crunch, and global brand consistency. It all starts with the Consumer Insight Team, which continuously analyzes sales data, social media trends, cultural food movements, and even fine dining innovation to identify gaps or opportunities in the market. A spike in interest around birria tacos, for example, might inspire a spicy beef consommé Doritos concept. Once a viable trend is spotted, food scientists and flavor chemists work alongside marketing strategists to develop flavor direction briefs, detailed documents that outline the intended taste profile, emotional positioning, and target audience. In PepsiCo's Flavor Innovation Centers, teams begin with flavor mapping. This involves breaking down target flavors into their basic aromatic and taste components. For a concept like Flamin' Hot Dill Pickle, the scientists would analyze heat components, acidity, herbal notes, and salt balance. Using GCMS, flavor chemists extract and replicate aromatic profiles to ensure they match real-life foods as closely as possible. Next, benchtop seasoning blends are created in small batches using food-grade flavor powders, encapsulated oils, anti-caking agents, and natural extracts. These are applied to test chips using miniature tumblers that mimic the behavior of full-scale seasoning drums. Each test batch is evaluated by sensory panels, trained tasters who assess flavor intensity, balance, aftertaste, aroma, and how the flavor interacts with the chip's natural corn and oil base. Their feedback is mapped against a flavor wheel to identify gaps or off notes that require reformulation. Multiple iterations are often needed. Some spices may clump, certain acids might degrade in heat, and some flavor oils could lose their punch after just a few days in packaging. Stabilizers and carriers are used to protect volatile components, and microencapsulation techniques ensure that heat-sensitive ingredients only release during mastication, not while sitting in the bag. Once the flavor passes internal panels, the next phase is consumer testing. In select cities, Doritos organizes blind taste tests, sometimes with up to 500 participants per flavor. Reactions are scored not only on flavor, but on memorability, uniqueness, and potential repeat purchase behavior. Statistical modeling software crunches this data to identify the most promising formulas. When a flavor is approved, it must be scaled up to factory levels without losing its integrity. Seasoning blends are manufactured in industrial blenders, often in batches of hundreds of kilograms. The bulk seasoning is tested for particle size, uniformity, moisture absorption, and flow behavior. During this phase, the seasoning is often reformulated slightly for stability, color consistency, and performance under high-speed drum tumbling. Then come the pilot runs. A limited quantity of chips is produced on a full-scale Doritos line using the new flavor. This lets engineers monitor how the seasoning behaves under actual production conditions, how well it sticks to the chip, whether it builds up on machinery, how the oil in the powder affects packaging line sensors. If issues arise, tweaks are made not just to the formula, but to the machinery settings as well. Finally, once all checks are passed, the new flavor enters full production, often accompanied by bold marketing campaigns and timed releases. Global coordination ensures that ingredients meet regional compliance, and new flavors often debut in test markets before rolling out broadly. These launches are tracked in real time, and consumer response loops back into the development pipeline, influencing which flavors stay, evolve, or disappear. This highly coordinated, scientific, and iterative approach allows Doritos to launch daring new flavors while maintaining the consistency and production efficiency that a global brand demands. Each new taste starts with creativity, but ends in finely tuned, factory-scale execution.